Test. Hallo Matthias, hörst du mich?
Starting from very simple things and try to make it more a classroom setting. Today we have a couple of different topics, quite different ranges with presentations. Some of the presentations will lead to extended mini symposia tomorrow. If you are particularly interested in some topics, go to the speakers and ask what they're doing and if you want to see more details about this. People can put material into the chat, so you find some links or notebooks or zip files whatsoever in the chat of the user meeting. Have a look there if you something popping up there. Ask questions whenever you're interested in the topics. Program is a little bit flexible. And the first blocks, the first speakers are Michael Neuenteufel and Jürgen Frohlwitz, sharing the first presentation on curvature.
Yeah, thank you very much, Joachim. So today I will talk together with Evan about what we can do with ngSolve with respect to surface PDEs. So we will start with a very simple example with the Poisson equation on surfaces, and then go also on more complicated. So now with Stokes equation on the surface, how can we do tangential vector fields on the surface? And then also a big part will be about how to approximate extrinsic and intrinsic curvatures on surfaces which are not smooth, and how good does it converge. And then we apply this also, for example, to shell problems. We have a thin-walled structure, and we want to simulate how the shell gets deformed if we use only the mid-surface. Doesn't work? Okay. Okay, so let's start very simple. So what changes if we have found element method working on flat case? How can we extend it to a surface? So let's start with a reference triangle, and we have a deformation to an affine, or maybe also curve triangle, also in a flat 2D setting. So we have our transformation phi and the Jacobian, a 2x2 matrix, and the Jacobi determinant. And to compute the mass matrix, we simply go back to the reference triangle. We get the modulus of the deformation determinant. So if you think of a scalar h1 function so far. And for the stiffness matrix, so if you have here the gradients of the test and trial functions u and v, we do also have the chain rule. So we get also for the pullback, we get the Jacobian, the inverse also inside. So this is standard. So what changes if we have now a mapping from the reference triangle to a surface, maybe curved element? So first of all, the mapping goes now from R2 to R3. And so the Jacobian is a 3x2 matrix. So it's not a square matrix anymore, so we cannot take the determinant like we did here. But we can still consider the surface determinant as the square root of the determinant of F transpose F. which is also the Frobenius norm of the cofactor matrix of F if we have the extended 3×3 matrix here. So for the mass matrix, nothing really changes. We just replace the determinant with the surface determinant. And for the stiffness matrix on the surface, so this will be in fact the surface derivative. Now the inverse is not well defined anymore because it's a 3×2 matrix, but we can, as it has full rank, so we assume that it's not degenerating the transformation. Then we have the Moore-Penrose pseudo inverse, which can be computed like this: F transposed F inverse F transposed, and we use this here for the mapping back. So we can now assemble the mass matrix and the stiffness matrix on surface elements. And this is all we need to solve a Poisson problem on the surface. So here we have the surface derivative of u. On the surface should be some right-hand side f, some force, and we can also prescribe Dirichlet boundary conditions. And tomorrow in the hand-on sessions we will also see how this is implemented and play around with all the examples I present here. Okay, so the reason also why this works like I presented here is that if we have Lagrangian finite elements, or also discontinuous L2 elements, we can map it from the reference element to the physical ones more or less 1-to-1. So u is a function on the deformed, or on the physical element, and u hat on the reference element. And with this mapping, the continuity condition is not destroyed, so this works well. And for discontinuous elements, we don't care about continuity conditions. Maybe one small remark is also that it's good to have isoparametric elements for the discretization. So if we curve the surface with order k, then we should also use polynomials, Lagrangian finite elements of order k, to have enough polynomials on the surface to have a good approximation property. But I don't want to go into the details of approximation properties on non-affine deformations. But still there's some open questions. So if we now have, for example, H-diff conforming Gravier-Thémard or H-curl conforming Netherland elements, how can we do this mapping on the surface? And also, can we generate some tangential vector fields, so vector fields which live only on the tangent space of the surface and don't have a normal component? And therefore, let's again go to the reference triangle in the flat case. So if u hat is an H-curl conforming Netherland elements on the reference triangle, and v hat an H-diff conforming BDM or Gravier-Thémard element, then we can define with the covariant mapping here function u living on the physical element, which preserves the tangential continuity by this mapping. So this is standard. And for H-diff conforming elements, we use the Piola transformation, so 1 over determinant and the Jacobian, to preserve the normal continuity when going from the reference to the physical element. So what do we have to do when we go to the surface? This is more or less the same as before. So we replace the inverse with the pseudo inverse. So then we have a covariant mapping from the reference to the surface triangle. And for the Piola transformation, we only have to replace the determinant by the surface determinant. And then we get also a Piola mapping from the reference to the curved surface element, and the normal and tangential continuity gets preserved. And as a nice side product, also we now defined tangential vector fields on the surface, because we can think of these u hat and v hat as tangential vector fields on 2D. There we don't have any choice. And we know that f acts like a push forward, and also the pseudo inverse transpose, so they're mapping tangential vectors to tangential vectors. So this is an easy way to construct tangential vector fields on a surface, so they don't have any normal components. Maybe also a short remark, how are surface finite elements implemented in ngSolve? There are somehow two types. So the first type is if we have, for example, Lagrangian finite elements on a tetrahedron and we restrict it onto a triangular face, then we see that this restriction leads to a valid 2D triangular Gaussian-find elements. The same fits for H-curl conforming Nedelec elements. Then we have also the Reggie-find elements, H-curl, and the number space is of course just a number, so we don't have to do very specific, we just take the trace. But for these kind of elements we really need to construct somehow new elements with this mapping from the 2D reference element to the surface element. So discontinuous L2, H-diff conforming Rabe-Tomar BDM, H-diff Helland-Hermann-Johnson elements we saw yesterday for the Kirchhoff-Love plate for the fourth order problem, and all these facet spaces for hybridization, hybrid discontinuous Galerkin method also needs to be mapped from the reference triangle. But with this at hand, we can also go to more complicated equations like the surface Navier-Stokes equation we see here on the curved domain. So here we have that the velocity should live really in the tangent space of the surface, and P will be the projection onto the tangent space, so identity minus the dyadic product of the orthonormal vector, and epsilon s is the symmetric covariant surface derivative of our vector field u, so it really acts only on the tangent space. So if I multiply the normal from the left or right, this would be 0. And here we see the surface Navier-Stokes equations. More or less the important thing is that we have here projection, and all our differential operators are now with respect to the surface. And tomorrow we'll present also how to use the H-diff conforming HDG method to set up this example here. We already had yesterday this kind of method on flat case. The nice thing about this is that we use H-diff conforming elements for the velocity u, which leads that we get exactly divergence-free solutions also now on the surface. So really pointwise divergence-free solutions, which is very nice. Okay, another bigger topic is curvature approximation, because most of our surfaces will try to approximate a smooth surface, and on a smooth surface we can compute the Weingarten tensor encoding all curvature informations. As we see, if we have a surface here and the normal vector changes, then this indicates that there's some kind of curvature. But if we now have an affine triangulation like this, so we have here two affine triangles, then the normal vector will be piecewise constant, so taking the derivative would lead to 0. But we have a jump of the normal vector. So there's a question, how should we define a Weingarten tensor on a discrete surface? And it's known from discrete differential geometry, for example, that this dihedral angle can be used to approximate the curvature on the surface. And this motivates us to define a distributional Weingarten tensor acting on a test function sigma, where we compute element-wise the Weingarten tensor, and on all edges we have the jump of the normal vector, and it hits with the element normal component of sigma. Sorry?
Can you say a few words about the Weingarten tensor for people who have never seen this? Like second derivatives?
Yeah, so to compute, yeah, right. To compute the normal vector, if we have an embedding, then we need can take the cross product of tangential vectors to compute the normal vector. So it's like we need the first derivative of the embedding. And so if we then have the normal vector and take another surface derivative, so that's then second order differential operator with respect to the embedding. So later on for surfaces I will present, this might lead to a fourth order problem, because if we have a displacement of our shell or describing our surface, then this will be a second nonlinear differential operator on the displacement, and this leads to some problems. And yeah, and Therefore, we want to first have a distributional Weingarten tensor. This will then relate to the Helen-Hermann-Johnson method also. And for sigma, we will use these Helen-Hermann-Johnson find elements we saw also yesterday, shortly in the Kirchhoff-Love plate, which are symmetric, and this normal component is continuous. So here I also wrote down the definition. So H1 and Hdiff we already had yesterday several times. So for Hdiff we have that the normal component, so BDM for example, that the normal component should be continuous over elements, but the tangential components might jump. And this Hdiff or Helen-Hermann-Johnson space is defined as matrix valued L2 functions, where if I take the divergence 2 times, this gives me a scalar, and I require it to be in H-1. And this Helen-Hermann-Johnson space is we take piecewise polynomials for symmetric matrices, and if we multiply the normal from the left and the right, so we take the normal component, then we require that only this scalar is continuous, so does not jump. So the normal tangential and tangential components are allowed to jump, and here we see the lowest order degrees of freedom, so the normal components of piecewise constant elements. Because the idea now is that if we have a distribution, we can compute like with an Ries isomorphism and L2 representative by computing a mesh matrix, solving it, and then we get a lifted Weingarten tensor encoding all the curvature of our discrete surface, and we can ask ourselves how good does this converge to the exact curvature. And we can try it out for a fine triangulation and using piecewise constant Helen-Hermann-Johnson elements, and we see that in the L2 norm it converges linearly, so this is the best we can expect with piecewise constant elements. And if we go to a polynomially quadratically curved surface, so still not C1, although it might look like that, and use linear approximation, then we see quadratic convergence, and it would get better if we increase the order of curvature and approximation space. And here we see that it holds for elliptic, hyperbolic, and parabolic domains. And this we will also test tomorrow, for example. And one application of this curvature is Coiter shells. So for shells, we have a very thin-walled structure, and we don't really want to mesh and solve the equations on this geometry. And so the idea is to only serve the mid-surface, here indicated in red, and derive by asymptotic analysis equations on the mid-surface. And one of these are the nonlinear Coiter shells. There's also an Acti or Reisner-Minlin shell equations, including the shear. But for Coiter shells, we only have the displacement u, how the mid-surface gets deformed. We have the thickness and some material tensor. Then we have the deformation gradient, like in elasticity, but now on the surface restricted. And here we have the green strain tensor restricted on the tangent space of the surface. And so the first energy is the membrane energy, so this is the green strain tensor. So how we stretch our shell. And the second term here, we take the difference between the Weingarten tensor of the initial and the deformed configuration. And so the difference of the curvatures corresponds to the bending energy of our shell. And as we see now here, we have here the Weingarten tensor of the initial and deformed configuration. And if we saw before, if we have an affine triangulation, this is not well defined. Also, this would lead to a fourth order problem, because you have the Hessian of the displacement u involved and then squared. And I can solve this problem by using now this lifting procedure of the distribution of Weingarten tensor, by applying it on the difference of the two Weingarten tensors of the initial and deformed configuration. I do a lifting from this part and this part with our Lagrange multiplier sigma to a new L2 unknown, and I use this for the bending energy here. So this is like a free field formulation, and sigma is the Lagrange multiplier having the physical meaning of a moment tensor for the experts. And we can also eliminate the additional lifting here if M is invertible, leading to a mixed saddle point problem, but only second order. So we could get rid of the fourth order problem. And the nice thing is that if we now linearize it, so we assume that we are in a small strain regime, and if we assume that we have a plate, then this reduces to the Hellon-Hermann-Johnson method for linear plates we saw yesterday. So this is somehow an extension of this nice mixed method from linear plates to nonlinear shells. And we can also use hybridization techniques and so on to get rid of the problems of saddle point problems. And tomorrow we'll show how you can set up such an example. So we have a strip which is fixed on the left, and on the right we apply a moment such that at the end it should perform a perfect circle. And we also see some tricks like how can we get rid of locking. Here we have linear elements, and this is cubic displacement elements. And of course we can try to increase the moments. It's non-physical, but we see that the linear moments start generating nice stars, and after about 7 rounds we see a self-intersection, and then at some point Newton's method just doesn't converge anymore. So we can try out this tomorrow. And now I will hand over to Evan for the second part.
Thanks. Okay, so I'll finish up the last few minutes of this talk speaking about two other notions of curvature that one can compute on surfaces using ngSolve, namely the Gaussian curvature and the mean curvature of an embedded surface. So the setting is the following. I'll consider a surface S with unit normal nu. I'll let tau1 and tau1 be an orthonormal basis for the tangent space to the surface at a point on the surface. And consider this matrix that I've defined here. Aij is defined in this way. And if you look at the eigenvalues of this matrix, it's a 2x2 matrix. It has two eigenvalues. They're called the principal curvatures of the surface. The Gaussian curvature is the product of those two principal curvatures, and the mean curvature is the sum of those two principal curvatures. So it's the determinant of A and the trace of A. An important fact about the Gaussian curvature is that it's an intrinsic measure of curvature. So it's a quantity that does not depend on the particular embedding of the surface in R3, but it just depends on this quantity, the metric tensor, which is if phi is the map from the reference domain to the surface, the metric tensor is the gradient of phi transpose times the gradient of phi. So this Gaussian curvature K is an intrinsic quantity, so it only depends on the entries of G and its derivatives. One of the implications of that fact is that if you have a surface with a given Gaussian curvature, and you deform it isometrically, in other words, you deform it in a way that preserves this metric, then the Gaussian curvature will not change. So, for example, this plane right here has Gaussian curvature 0. If you deform it into a half cylinder, it still has Gaussian curvature 0 because you haven't changed the metric. In contrast, the mean curvature is an extrinsic measure of curvature. You cannot compute it just from G alone. You need other information about how the surface is embedded in R3. So the mean curvature of a plane is 0, but when you roll it into a half cylinder, it's no longer 0. Likewise, if you take the surface of a sphere that has non-zero Gaussian curvature, because it's not possible to isometrically deform a sphere onto a plane. This is why when you look at maps of the globe, they never look quite the way you would expect them to look. There's some distortion. So I'll spend a few minutes just giving a little bit of background about the Gaussian curvature, and then I'll talk about how to compute it on triangulated surfaces. So first, let's talk about a smooth surface without boundary. One of the important features of the Gaussian curvature is that if you integrate the Gaussian curvature over the surface, you end up getting a topological invariant of the surface called it's 2 pi times this quantity called the Euler characteristic of the surface, which can be defined in a number of different ways. One way is to triangulate the surface and then take the number of vertices minus the number of edges plus the number of faces. You can also define it to be 2 minus 2 times the genus of the surface, where the genus is roughly speaking the number of handles in the surface. So for example, a sphere has Euler characteristic 2 because the genus is 0. The torus has Euler characteristic 0 because the genus is 1, and so on and so forth. If you have a smooth surface with a boundary, then this so-called Gauss-Bonnet theorem, that identity that I wrote down on the last slide, gets modified in the following way. So the total Gaussian curvature integrated of the surface is equal to 2 pi times the Euler characteristic of the surface, but there are the extra terms here that arise that come from the curvature of the boundary. So here you have this extra term, the integral of the geodesic curvature over the boundary of the surface. So that's basically a measure of how quickly is the tangent vector to that curve rotating as you move along that curve. So it's the tangential derivative of the tangent vector dotted with the unit conormal vector. That's called the geodesic curvature. And then this other term that appears in the Gauss-Bonnet theorem is measuring how quickly does the tangent vector turn at the corners of the boundary of the surface. So that's the Gauss-Bonnet theorem on a smooth surface with boundary. So far I've talked entirely about smooth surfaces. What happens if you're on a triangulated surface? How can you make sense of the Gaussian curvature in that setting? It turns out that you can still make sense of the Gaussian curvature of a non-smooth surface in the sense of distributions. The way it works is as follows. So first, let me give the definition in the case where you have a piecewise linear triangulated surface. So if you have a piecewise linear triangulated surface, then you should think of the Gaussian curvature as being a distribution supported on the vertices of the surface. You have Dirac deltas centered at each vertex. So the way I've written it down here is that the action of this distribution k on any test function phi is given by a linear combination of the values of phi at the vertices, weighted by what's called the angle defect at that vertex. So what's the angle defect? The angle defect is what you get when you visit that vertex and you take 2 pi minus the sum of the angles incident at that vertex. One can motivate this definition of Gaussian curvature on piecewise linear surfaces using the Gauss-Bonnet theorem. So the way you do it is you say, well, the total Gaussian curvature integrated over this region here, according to the Gauss-Bonnet theorem, that's 2 pi minus the sum of the turning angles when you go around this loop here. And it turns out the sum of the turning angles is the same as the sum of these angles incident at V. So the Gauss-Bonnet theorem can be used to motivate this definition of Gaussian curvature for piecewise linear surfaces. What if you have a piecewise smooth triangulation? So imagine instead of using piecewise linear, imagine instead of using straight triangles, you use curved triangles with some polynomial order. Then the definition of the distributional curvature gets modified a bit. You still have these angle defects at vertices, but you also have additional terms corresponding to, you have the curvature in the interior of each triangle, so that's well defined in the classical sense. And then you also have terms that arise along each edge. You end up getting jumps in the geodesic curvature across the edge. That term can also be motivated with the help of the Gauss-Bonnet theorem. So this is the way that one can define the Gaussian curvature of a piecewise smooth triangulated surface in the sense of distributions. If you want to do some computations, then you might want to lift that to a finite element space. In other words, compute an L2 representative of that distribution. So the way you would do that is as follows. If you're given a triangulation that has, say, curved triangles with polynomial degree k, you're going to seek a scalar function, which I'll call kh, belonging to a Lagrange finite element space of a given degree. I'll call it degree q, say, such that for all test functions phi in that same finite element space, this equality holds. And one can prove error estimates for the convergence of this discrete notion of Gaussian curvature to the exact Gaussian curvature under refinement of the triangulation, and the rates are written down here. I should say that the rate that I wrote down here comes from a paper that I wrote about approximating Gaussian curvature, not for embedded surfaces, but for planar domains equipped with non-Euclidean metrics. And then I translated those estimates to this setting. They're not necessarily sharp in this setting, and understanding the precise convergence rates for embedded surfaces is something that's ongoing work. And then this last slide here, I'll say a few words about computing that other notion of curvature that I mentioned several slides ago, which is the mean curvature of an embedded surface. So recall the definition of the mean curvature. Remember, the mean curvature was the sum of the principal curvatures rather than the product. And there's actually a nice useful identity that one can use to compute the mean curvature on any triangulated surface. It turns out that the mean curvature times the normal vector ends up being the same as the Laplacian of this vector field I'm calling the identity vector field. So what is this identity vector field? It's the vector field which, at any point on the surface, you associate to that point the position vector of that point. So that's a map from S to R3. So it's a vector field on the surface. If you compute the surface Laplacian of that vector field, you get the mean curvature times the normal vector with a minus sign. So this motivates, there's a very natural discretization of mean curvature, and it leads to a natural discretization of a curvature-driven flow on embedded surfaces called mean curvature flow, which is a differential equation that governs the evolution of a surface. And the setting is that the velocity of each point on the surface is proportional to the normal vector, and the constant of proportionality is the mean curvature. So that's a curvature-driven flow that's often studied in applications. And here's a natural discretization of that. You just discretize the Laplacian in the natural way, and you discretize the other term in the natural way with finite elements. So this is something that goes back to work by Zug in the 1990s. And this is a computation done in ngSolve where this system of differential equations was solved numerically in ngSolve. So in the tutorial that Michael and I will present, we'll talk about this example of doing mean curvature flow with finite elements, and we'll talk about computing Gaussian curvature with finite elements as well. So with that, I'll conclude. Did you want to say a few words about the tutorials, or shall we wrap up there?
It's fine. We wrote down the topics of tomorrow. We can discuss. Yeah, hopefully we'll see you in the tutorials tomorrow. So thank you for the attention.
Thank you.
Short comment on this. If you are not so much in differential geometry, all these terms look a bit scary, but when you really can compute them and look at them, I think you get a much better understanding what this different types of curvature really means. Yeah, I think it's a good propaganda for the minute tomorrow, and then you can compute all of this tomorrow. And I think we.
Well, I think he's next.
Kusheng is the second one. But thank you again. You've seen some first multi-grid tutorials yesterday on how you have to work with prolongation and combine things together to get multi-grid for the Poisson equation in Jay's tutorial. Kusheng will show more complex situation, H12 function spaces, how to build grid transfer operators there, how they perform in different problems. We'll show also how to add these prolongations which were not in ngSolve before. So we got in contact with Kusheng a couple of years ago when these prolongations were missing, and Kusheng worked hard and got them also around and showing us.
Yeah, thank you, Yahim, for the invitation. So mainly today I'll talk about this Crozat-Ravia prolongation, not the H-div and H-curves per se. But our main interest is in designing a good solver for HDG method for say diffusion and the Stokes problems, and we have some operator preconditioners, and then after that we decided to look into multigrid. And when we first start to work on the problems, there are not too many work on multigrid for HDG methods. So So let's see what we have. So everything for this presentation, everything starts with the Crozat-Ravia method. The scheme is very easy. You're solving diffusion problems, then your space is a non-conforming finite element, piecewise linear. They are continuous in the midpoint. And for these schemes, if you have a hierarchical mesh, then you can construct a multi-grid algorithm there. Basically, you need to find a smoother and a prolongation operators. And because the space is non-nested, the prolongation is not a simple, a natural extension. So you need to do some sort of average. Here is how we do average on from these black two triangles. So that's the coarse mesh. Then I put a bisection here. So the fine mesh has these small triangles. Then the degree of freedom are these red dots. So how do you prolongate from the coarse to fine? And so basically in 88, 89, Subrena and they show that you just do average. If you want to get the value here, you just take the value on the left triangle and the right triangle and take average. On this type of mesh, the value at U will be linear combination of all 5 degree freedom on the big elements. And if you are in the interior edge, then it will be just an average of V2 and V3. So that's a 2D case. In 3D case, you have a little bit more work to do to implement this prolongation. I think that's I spent quite a lot of effort to put that in ngSolve. But as long as you have the prolongation operators, then you can design this multi-grid algorithm easily. The smoother is just you do a point Jacobi, or you can do this block version, and then you restrict, then you do a coarse grid solve, you prolongate, then your multi-grid algorithm will be working. So that's this Crozat-Ravia. I'll show you a code to do that in tomorrow's tutorial. And then we extend to this HDG method. So basically, we still solve the diffusion problems. And now we write the Poisson equation in a first order form, and then we just do integration by parts. So we have this three-field formulation. Jay is very familiar with that. So we have this three-field formulation. It's called a mixed form of the HDG method. This red guy is the numerical flux, and this the blue guy is stabilization operator. So the lowest order scheme we do is we take the alpha to be 1/h times projection, L2 projection onto the faces space, which is called M. And the choice of degree of freedom, or the spaces we have is sigma is a vector, you take piecewise constant. Interior part of VH is you take the piecewise linear, and then on the global variable on the edges, you take it to be piecewise constant again. And that's this method. So for HDG, we can do static condensation. You get rid of all these black dots, then you end up with a linear system for the 1 degree of freedom per edge, which is share the same degree of freedom as Crozat-Ravia. So you can use the same prolongation operators, and then you can use the very point smoother. So with this, it seems the multi-grid is very easy for this HDG method. You just use what you have for the CR to do it in here. And actually, this is kind of a known fact. We know that Crozat-Ravia is equivalent to Ravetoma in the lowest order case, and actually it's also equivalent to our lowest order HDG method. And now we really do not need to do any theory on the multi-grid part. basically we can show that the matrix or the linear system for Crozat-Ravia is identical to the HDG condensed linear system, and it's also independent of our stabilization parameter as long as you have that projection operator there. So we can use this multi-grid serial for Crozat-Ravia to apply it to HDG, and then on top of that, when you have a high order method for HDG, you can increase the polynomial degree. Then we can use a block smoother to first reduce the polynomial degree to the lowest order case, then use the low order multi-grid solve. So yeah, that's that. And we can do a posterior error estimation for the schemes. It turns out that there's a HDG version that we did with Mark Ainsworth in 2018, and here is the earlier versions. At that time, we don't know they are the same, and actually these two guys, they're exactly the same. This is called the guaranteed error bound in a posterior error estimate, and this guy can be used in driving our mesh adaptation. So we implemented this HDG method in ngSolve. I think, yeah, this test Joachim showed yesterday, and we had 2D version and 3D versions. We do multi-grid plus adaptive mesh refinement using this posterior error estimator, and we had 2D results. These numbers are not easy to see, but the main message is that multi-grid is pretty robust. The iteration count after a couple of runs, I think it's less than 10. And the condition number is 1.47. This problem has a high contrast diffusion coefficient, but the multi-grid also works pretty good. And here the smoother I used a very expensive smoother. It's vertex patch, the block Gauss-Seidel smoother. In terms of iteration count, it's more efficient than a point Gauss-Seidel smoother, mainly due to the material heterogeneity. And so we have a similar results in 3D using this adaptive bisection refinement. And the condition numbers are kind of bounded, so iteration count is robust with respect to mesh refinement. So we get a robust multi-grid for the lowest order schemes, and then we extend that to Stokes. For Stokes, we do a penalty formulation. So we just the continuity equations, you add an epsilon there. Epsilon will be a small number, and then you can convert this mixed formulation to a singular perturbed primal formulation. You end up with an SPD system, but there's a singular perturbed divergence operator, graditive operator here. And then we still want to do multi-grid, and the Schubert has, Joachim has two ingredients, which is the smoother and the prolongation. Smoother has to be robust with respect to the HDiff kernel, and the prolongation has to also respect the divergence-free functions. And so for the smoother, I had two pieces. For the smoother, we just do a HDiff based smoother. So either in 2D you can do block vertex patch block. In 3D you can do edge patch or vertex patch. And for the prolongation, we have a little bit more work to do. So this is the Crozat-Ravia element. Previously, our prolongation is just by average. It turns out that that average prolongation operator is not robust with respect to the divergence-free functions. It does not map the coarse grid divergence-free function to fine grid divergence-free functions. And if you use that prolongation, the overall multi-grid algorithm is not stable. It's not robust with respect to the singular perturbed parameter epsilon. And then we follow the Yahim's suggestion to do a two-step procedure. You first average, and then after you average, you will take care of I think the divergence-free part on the boundary of the triangle, and then after that you do a local correction, which they call it the harmonic extension. You do a local correction. It's a local, like in here it's a 3x3 system solve to remove this divergence-free part, to remove the divergence interiorly. So that this is that's a harmonic extension. So our actual prolongation will be the average plus this local correction. Local correction is very cheap, and then we did that for HDG. We still do a three field formulations, and no, there are 4 fields. You have introduce G as the velocity gradient, then you just do integration of parts, and you put derivative to the test functions. You basically have the same thing, and you can show that this schemes is identical to the Crozat-Ravel method. If you use the choice of find elements. So for velocity, you take it to be linear. Everything else you take it to be piecewise constant. And then this method is the same as Crozat-Ravel. So you can use the multigrid I introduced to do that, to solve these systems. And yeah. So for a comment on high order, you just use for the block smoothers. There's a theorem by Yahim. If you basically the same said if you use that smoother and that prolongation operators, then the W cycle multigrid will be robust, and the variable V cycle will also be robust. I think we prefer to use this variable V cycle. And yeah. So I think I comment that these results are not available in the literature yet, but I wrote this like 2 years ago. So I think Yahim has an unpublished paper in his webpage, and in there's one line commenting that his multigrid approach can work with Crozat-Ravel elements. Your paper mainly is on P2, P0 final elements, but it's yeah, but then there's unpublished notes mention about the Crozat-Ravel elements. Anyway, so we implement that this works, and we solve this Stokes cavity problem using the HDG method. I take epsilon to be 10 to the minus 6, so in the penalty parameter. And to solve the problem, we use multi-grid as a preconditioner in the CG algorithms. And I think I compare with V cycle, variable V cycle, and W cycle. And they are similar. They're pretty robust with respect to the mesh refinement. And yeah, so I think like maybe in the next 5 minutes I mention about another HDG method, this divergent conforming HDG or divergent free HDG method for Stokes flow. And it's basically here we just change the HDG formulation, change the spaces. For the velocity space, we require it to be HDiv conforming, this guy, for the local velocity space. And then for the finite space on the facets, we take only the tangential component. So my lowest order HDiv HDG method is this guy. There are 2 degree freedom on the edge, and the Crozat-Ravel method also had 2 degree freedom on the edge. And the previously not divergent conforming method also had 2 degree freedom on the edge. And basically we can show that this guy, previously I claimed that this HDG or called HDP0 is the same as Crozat-Ravel. Now you can show that this guy is also the same as that, except that you need to do a pressure robust reconstruction. And that's the Crozat-Ravel with the pressure robust reconstruction. You put a Ravel-Thoma projection on the right hand side. So this beta term is a mass matrix. If you don't have mass matrix, you just put the Rarotonga projection on the right hand side, and then that gives you the pressure robust Cruzat-Ravia element, and you can show that this guy is identical to my HDG method. So basically, you can use everything we have for HDG for the Cruzat-Ravia to precondition this HDG, this divergence conforming HDG method. Yeah, and I think there's a multi-grid when what do we do for Poisson degree which is greater than 0? So I have a multi-grid algorithms. I just cut and paste this algorithm from our paper. It's basically you have a smoother this we call pre-relaxation. It's I don't know what that is. So you have a low order space correction. This guy is the piecewise constant multi-grid part, and this relaxation I think it's doing a block smoother on the Poisson degree. Yeah. So using these algorithms, and that's it. And
Thank
yeah.
you very much. And I think you have prepared some material for
yeah, so
on programming some non-standard prolongations, and so you have to get into ngSolve. You have to do that on the C++ programming side. We started. You see, find some hacks by Gusheng and how to get this.
Yeah, basically, we have a small snippet in C++ to do these Cruzat-Ravia prolongations. I think I need to go into these mesh data structures to get something done. Maybe, yeah, maybe this guy. And I think I will show how to do these things tomorrow. Yeah.
Yeah. If you
okay.
want to see this, talk to Gusheng today or tomorrow.
Yeah.
Thank you.
Yeah.
Thank you very much. John Walker talking about non-linear vector spaces, but some Lie groups stuff is fine.
No, there's
okay,
no.
but non-linear space.
All right, so do this. So it's okay. All right. Okay. Okay, so I'm never really sure how to give a talk like this where you're supposed to actually show the gory details of how you really computed it. Normally that's all hidden. Anyway, so talk about a project. This is joint with Thomas Surovich. He was at the University of Magdeburg in Germany, but he recently moved to Simula. So this is doing optimal PDE control of the Landau-Dijen model. And this is, of course, using ngSolve to do that. So I don't really have a lot of time to go into where this model comes from. just use the arrows here. Okay. All right, so this model is meant to represent sort of the average sort of orientation of liquid crystal molecules. So these are usually idealized as these elongated rods. Of course, they're really molecules, and so you have many of them in a small location of space. And so we're not really modeling them at a, say, a microscopic or nanoscopic level. We're using more of a, say, a mesoscopic model. So these things have lots of applications, like in optics, of course, LC displays, and it's because they polarize light, along the axis of the molecule. But they have a lot of other sort of more modern applications in, say, material design. So one example is sort of colloidal particles that are sort of submerged or immersed in a liquid crystal. And so the way to kind of read these pictures is these line segments kind of represent the molecule orientation. So anyway, you can take advantage of this to have these things sort of aggregate into sort of regular patterns. So these are, again, these colloidal spheres. And so you're basically using sort of energy minimization to kind of guide this assembly. The sort of thick blue curve here represents a region of defect. I'll kind of explain a little bit about what that is. All right, so what are defects? So these things have sort of a fiber-like structure to them. And so you can kind of see the defects here and here. So this is where there's no real kind of net orientation of the molecules. And so in this case, this is a -1 degree defect, this is a +1 degree defect. You can also have half integer order defects, and so the two examples are given here. So again, you kind of see this fiber structure. This is not actually a liquid crystal, but it kind of illustrates what defects are. What does the degree mean? So this is some examples of that. So here I defined a vector field in the plane, like so. And so this is a half, so this is actually a +1/2 degree defect. So I visualized it here by removing the head of the arrow. So these are vector fields, but then we view them as line fields. So there's no forward back. Well, there's no difference between forward and aft symmetry. Similarly, this would be a -1/2 degree defect. This is a +1 degree defect. A saddle, -1 degree defect. You can up the degree, of course, +3 halves, -3 halves, and so on. And the main thing is, in applications, in actual experiments, you usually get, say, half degree defects, and these are not orientable. So again, these are plus or minus 1/2 degree defects, and if you try to give some kind of vector field orientation to it, you can't do it. So you need to use a model that somehow respects this symmetry of the problem. So again, without going into any details on where this actually comes from, so Q is going to be the order parameter that represents kind of this average orientation of these molecules. And so it's in 3D, it'll be a 3x3 symmetric traceless matrix. And basically the eigenframe of Q represents kind of the probability distribution of finding these molecules oriented. Q can be what's called biaxial. This is where all the eigenvalues are distinct. Usually the state of the liquid crystal is in a uniaxial state, two of the eigenvalues are equal, and you can write Q in this form. And so here, the N here is what's called the director. And so that's kind of representing the line segment that indicates the orientation of the molecules. S here is what's called the degree of orientation. So if S goes to 0, this is supposed to be like a defect region. Anyway, so when I show the simulations later, I'm going to visualize the N, because trying to visualize a 3x3 matrix is a little bit problematic. So visualizing N, we're basically visualizing, say, the dominant eigenvector. All right, so the model comes from doing energy minimization. So we have some basically elastic energy. You could do, of course, what's called a one constant model, i.e. the Laplacian, or you can have a more complicated anisotropic elastic energy, which I'll show on the next slide. There's also a double well potential. There's some other terms. There's a surface anchoring energy, and of course, like a right-hand side forcing term. So I'll just go through these different pieces. So the elastic energy density, in a fair bit of generality, looks like this. So grad Q squared, the divergence of Q, a somewhat weird term shows up here. There's also a twist term, and this is meant to model of cholesteric liquid crystals where you have sort of a twisting motion or a chiral symmetry to the molecules. Anyway, so this is like sort of gory details of what these different terms are. So, of course, you don't want to really write these out by hand yourself, so I just make Python do it, for me. So I'll show a little bit about how you do that. Oh, actually, another thing so the Q here is fairly high dimensional. So in 3 dimensions, a symmetric traceless matrix. That's dimension 5. So when I do these computations, it's actually 5 coupled variables in 3D. So that's not a cheap thing to do. Another reason I wanted to use a good package that had good solvers and that kind of thing. Here's the double well potential. It's based on trace of Q squared. These are invariants of frame and difference, so that's why that shows up. There's kind of an illustration of what the double well looks like. So it's a little bit different than sort of the standard type of double well that you would see in Alan Kahn or Kahn Hilliard. It's kind of a lopsided double well. So we're going to be doing optimal control, where the boundary conditions are going to be essentially the control, as well as like a right-hand side force. But in the computations, I won't actually use that. So this is going to end up being kind of like a Robin boundary condition eventually. So I basically want to penalize the state of the liquid crystal to match some kind of desired state on the boundary of the domain. All right, so if you want to just do the equilibrium problem, take the first variation, set it to 0, derive the PDE, this is what you get, so semi-linear with the PDE. This just denotes taking the traces apart. Psi is, again, the double well potential. But this is kind of difficult to do optimal control on because it's not convex. So instead of doing that, we look at a gradient flow. So now we have a semi-linear parabolic PDE. Well-posed solution is unique, so you can do optimal control on that. Of course, things are a little bit more expensive now, because now you have to solve a time-dependent problem. So you can kind of view this. This is like a tensor-valued version of the Allen-Kahn equation. So this is the double well, different than typical Allen-Kahn, but we also have Robin boundary conditions, which isn't the typical thing with Allen-Kahn either. So if you're going to use ngSolve or a finite element method, you multiply by a test function, integrate by parts. This is the weak form. Here I'm just assuming that one constant elastic energy, but this could be the more general anisotropic elastic one. Here's just an illustration of what the output of the simulation is. So so we're viewing the dominant eigenvector of Q viewed as a line field, and it's colored by the dominant eigenvalue. So you can see the defect. And so here I'm doing optimal control to sort of force the defect into a particular location in the domain. And again, that's the gradient flow, yeah. All right, you do finite elements, the typical thing, right? Put H's everywhere. Here I'm just doing, low order, piecewise linear, Lagrange. Although obviously in ngSolve you can do higher order, without much trouble. The controls in the domain, just piecewise constant because these are posed in an L2 space, so you don't need to do anything more than that. Here we have, this is a nonlinear term, so we do fully implicit Newton's method. And again, you can do this either by hand or doing the automatic variation stuff in ngSolve. All right, so I wanted to show a little bit like how you actually, put this in to ngSolve without going to all the details. The code is somewhat complicated. So this is a symmetric traces matrix. I think ngSolve does have matrix valued like test and trial functions, but having the traceless part, I don't think that's built in.
As well as symmetric, it's a traceless matrix. I'm not sure whether symmetric plus traceless the same.
Oh, okay.
If it's missing, it's a small missing feature.
Right. But it's fairly easy to do it just by writing out a basis for symmetric traceless matrices. So that's just what I've done here. So you basically map capital Q to a 5-dimensional vector cube. And that's essentially how I do it in the code. So I just show a little bit. So here's like a subroutine just to give me a basis for symmetric traceless matrices. And I have a choice to either do it the NumPy way, because sometimes I have to compute things more numerically. So I'm just setting up matrices that represent these, or I need to actually make them a coefficient function so I can define the forms using ngSolve. And I have some other like little helper routines. I have to be able to map from vector Q to capital Q, as well as go the other way, map capital Q to vector Q, so on and so forth.
This is an identification between R5 and the symmetric.
Yeah, right. I mean, it's just it's just this. So, and this is an orthonormal basis with respect to the Frobenius inner product. So, the norm of Q, capital Q, is the same as norm of little q. And similarly for that, I mean, that's convenient for implementation as well. So let me show a little bit of the other stuff. I don't know, perhaps I overdo things when I implement them, but everything is, object oriented. So I have a class, LDG model, blah, blah, load up some meshes, etc. Okay, so then I have to define the finite element spaces. So what is that? So I get my basis, and that's stored. I define my 0 function based on the dimension. If you're in dimension 2, it's a 2-dimensional space. Dimension 3, it's 5. The finite element space is defined like this, and this, I think this was a bug I found eventually at first, because I had to have the dimension be different than the spatial dimension, and that wasn't, like, there was something wrong there, which got fixed. So anyway, it's H1, degree 1 polynomials, raised, you take, Cartesian product. You can write it differently. You can put in, I guess, dim equal 5 in here, but apparently that means something else, a different implementation. It's like a different ordering of the degrees of freedom, which has an effect on if you want to use algebraic multigrid versus geometric. So that was another issue that came up. Anyway, so that's how you have to do that. That's all I wanted. Yeah, so I also have to define my L2 space on the boundary. So this is a facet space. Degree 0. And then there's defined on, which you can't use here. You have to do this defined on bound, because it's only on the boundary. And again, this has to be raised to the number of components.
So,
yeah.
If you raise a finite element space to the 5th power, it's a product space of the same space 5 times. It's similar as you write v times v times v times v 5
Right.
times. And then the degrees of freedom are located first one, second one, third one. With the additional information that it is not just v times v times v. The
Right.
space knows that it's 5 copies of the same.
Right, that's the dim way. Use it doing dim, yeah.
Gradient, then it will take the gradient for each of the components.
Right, right. Okay, let's see what else that one. Oh yeah, so then I have to define the model. Okay, so I have my trial function, and these are, so everything's in terms of like the vector valued Q. And then I have another, so subroutine to compute stuff like the elastic term. So, which is in yet another file. So if I want to compute the L1 term, this one's easy. So in comes my trial and test function. I take the gradient. And then doing L1 is pretty easy. You're just taking the, I probably could have done inner product here. For the other ones, they're not as clean. So this has to get expanded out and you have to use the basis. So you obviously don't want to write this out by hand, but I just, it's easy enough to do that. Then there's the twist term. This is also a little bit of a mess. The twist term is like taking the curl of Q, so that's why the Levi-Civita answer comes up. And again,
okay, one comment here.
Yeah.
You're doing, I think, tensor operation. So you're multiplying higher order tensors.
Yeah.
Now we have coefficient functions which can be higher order tensors.
Well, that's what the basis is. The basis is, yeah. Yeah, this is like this. These are matrices.
Okay, I mentioned higher order. You can have third order, fourth order tensors also.
Sure.
And
sure.
you can do integer solve also.
Right.
And you can contract also. So maybe then you can remove the for loops, but use tensor contraction.
Oh, okay. Well, yeah, but it's also more clear when it's,
Okay.
I mean, you're right. Yeah, but then you have to know you have the right argument and the.
Yeah, the possibility for optimizations are better if NGSolve knows that it's a tensor, not just a big expression. But
Oh, okay. Yeah, but I mean, this is just computed once, though. Like, I define the forms once, and
okay.
that's it.
That's
Okay. But you're saying it makes a difference later?
It's already a third order tensor here. There's 3 indices.
Yeah, but I mean, this is just a NumPy. Yeah. Anyway. How much time? Okay, I'm still good. Right, then okay, so there's that.
Can I ask another question? Where can we find the code?
Well, I wasn't really making this available, so anyway, let's see. Okay, the double well potential. Right, so here, so this is where I had the trace of Q squared, the trace of Q cubed, trace of Q squared squared. So, if I'm computing the energy, here's the trace of Q squared, squared again. I do this mapping, I take my little q, map it to the big Q, multiply it 3 times, take the trace, inner product with the identity as the trace, and then I form my double well potential formula. Also the first variation and whatnot. So I ended up having the Newton's method kind of done somewhat manually. I've done the variation way as well. That also works. You can do that. It's not a big deal either way.
At the beginning, you have shown the NumPy computations, which are done once. It's a initialization, and then you're using the NumPy result for setting up the forms.
Yeah.
You're not calling NumPy for every element.
No,
it's
no.
done first, and then you get the big expression out of the NumPy.
Right. So this is just computing like little pieces of the energy and the form, and then here I get my elastic term, my time derivative term, double well potential, and then I have 2 parts of the model: the one that's integrated over the bulk, and then the one that's integrated over the boundary. So that's under define model, and then when you define the PD form, you just say call define model. This gives you the dx part and the ds, and then you set up, you know, like here I'm just computing the energy. That's I take, you know, have this variation, and then if I want my, you know, bilinear form, then I just, you know, and you have to say defined on the boundary for this ds. If you're doing Newton's method, you take the second variation. And also for, I guess I'm doing GM res, I think, and for this you need some kind of positive definite matrix that does act as the preconditioner. You can't just take the A form directly because it has a non-convex part, so that is just done to give me something to precondition with, etc. Set the controls. I think I already went through all of that. Anyway, so back to this just for a moment. I'll show the code actually running a little bit. So what are we trying to control? We're trying to control the state of the liquid crystal. So this is sort of the desired state that we want Q to have. And again, I'm just visualizing the dominant eigenvector eigenvalue. So ZC is like the target state. And then it's just doing tracking control as the objective functional. You want to minimize J, you know, with respect. So these are the controls. Q is the state, and of course is the PD constraint on the state. So we want to minimize the, you know, the least squares error here. And then just with, you can write this, you know, C is the space-time cylinder. It's for, you know, time dependent. So this is over the bulk. Over the boundary, although that's ignored usually, final time, and then just some Tikhonov regularizations of the controls. And then the controls themselves, so for the bulk term, which for the numeric I'll show, that's actually ignored. Just L2 for the boundary, they should be, you know, somewhat smooth in time, bounded to keep the sort of physical interpretation meaningful. For us, we actually take the boundary controls to just be constant in time. That's usually what the applications allow for anyway. It's just kind of for sake of generality. This is just an illustration of what the optimized control looks like on the boundary. So again, this is a finite element space that lives only on the boundary. It's the L2 space. Again, visualize the dominant eigenvector. This is the one that controls the plus 1/2 degree defect moving to the corner. And then you want to do optimal control. You have to, I'm not going through the details of this. So you have to control the state operator from the controls to the solution. You have to show this state differentiable because we want to do gradient-based optimization. So a little note about how you do that. So just think about formally differentiating the PDE with respect to the controls. So H2 would be the perturbation of the controls. This ends up getting another derivative on it. The rest of it was linear, so it looks the same. And then the usual thing of, you know, you rewrite the objective functional, the derivative, what's called the reduced functional, and then taking this derivative, you need what's called the adjoint equation. So that's given here. So this is a backward parabolic equation you have to solve. So I'll show a little bit how that works. So go back to optimization class. Again, a bunch of stuff here. All right. Yeah, so I have to be able to evaluate the objective. Okay, so I pass in my LDG, that class, that object. Okay, I do some stuff. And then, but to evaluate the objective, I have to, it's a time-dependent simulation, so I have to go through all the time steps. Here I'm reading those Z terms. So remember I had those Z targets, that was part of the objective functional. And little z, again, is this mapping back to the vector value case. And so, I mean, it's a little hard to read, but this is just basically evaluating the cost. Like that was the objective functional. So that's to integrate a bunch of these terms. Since some of this is time, like the controls are time independent, so those are sort of easy to deal with. But this is basically doing an integration in time. Then I have to add the final time cost. So that's here. These are just coefficients that came up in the objective functional. Yeah. Then I have to be able to evaluate the derivative of the control. So to do that, I need to solve the adjoint equation. So that shows up right here. So that's done elsewhere. So R is going to be my adjoint variable. So I integrate in time, and I form the derivative of the cost. So
You're doing also derivatives by hand, or are you using automatic differentiation?
well, it's not that hard to write this out. I mean, once you have the adjoint, the expression for, I mean, it's just this.
When the model becomes more complicated, then it might be
Yeah, sure.
automatic tools. And
Right.
what we can do now.
Yeah, sure. Okay, so I do that, evaluate the residual, main optimization loop. All right, then, yeah. So main optimization loop. So, okay, now I have to do an adjoint solve. So instead of setting an initial condition, you set a final condition. Then you run your adjoint backward simulation in time. And then this ends up getting integrated in time. Let's see. So bookkeeping. Then we have to get a descent direction. So it's basically just doing gradient descent on the objective functional. So this is just, all that does is it computes the L2 projection of the gradient. So if I go back, yeah, so get descent direction. So I just use the set command, actually. So this is my grid function that holds the direction, and then I just do a set on the terms that shows up in the gradient. And so, which is that's just what I needed to do. So I don't formally have to do a solve on that. Although typically you do have to do that. Then you do a backtracking line search because there's an inequality constraint. If I didn't have the inequality constraints, I could do a cubic bisection line search, which is actually pretty fast if you don't have the constraint. And for this, I just have like a generic backtracking thing written, so I can just pass it like the evaluation function or the cost function, and that's good enough. Then I think that's it. Let me just show a little bit of the adjoint. Alright, so this is kind of similar. So define PDE form, and it's almost the same thing as the forward problem. The only difference is for the double well potential, you have to take the second variation and so on and so forth. And you set a final condition, you run a backward adjoint simulation. So backward in time, so I actually do the time stepping in reverse. So I start at the final time and just march backward and just solve like you normally would. Although that's a linear problem, so you don't have to do Newton's method. Let's see, I'll probably skip this. Okay, so this is, this was one of the examples. That's the desired state. It's the optimized boundary control. It's the initial condition, and that's the final condition. So it matches the desired state. So I showed that one before. This one, the desired state is to have a plus and minus 1/2 degree defect actually separate. Because they have opposite charges, they usually want to combine, but if you choose the boundary conditions appropriately, you can actually force them to move apart. So I'll show an example. I'll show this movie. Okay, so if the boundary conditions were just say constant on the boundary of the box, they would just combine and there would be no defect anywhere. But because it's being optimized to not do that, they do move apart. Then here's a 3D example. Here we want the desired line defect. So basically you can kind of think of this as a bunch of plus 1/2 degree defects in each horizontal plane. And then this is a defect curve that goes through it. This is the optimized boundary condition on the box. To make that happen. So then this is the initial condition, it's the final, and that's the desired state. So it matches fairly well. And then this is just being colored by what's called the biaxiality parameter. I'm not going to go into that. I'll show a movie of this. All the movies are done in pair view, of course. All right, so let me show a little bit how. So originally I did the code differently, but because I did this update yesterday, which was kind of a nightmare, I had to redo this into a Python notebook or a Jupyter notebook. So this is the driver script. All those other little subroutines are living in their own files, but this is sort of the main thing. Just a little tip. So since I had all these sub routines, I had to keep constantly calling from ngsolve import, and so that was sort of overriding the draw. So luckily Christopher here told me what to do to address that. I want to skip through most of this. Here I'm just doing a 2D simulation because it's faster. There's the mesh. Kind of a plot of the initial guess on the boundary control. Set up an adjoint system, and then we do an initial forward simulation. So that's what the just the initial control is being used there. So it's not doing what you want to have happen. Let's see. Then sort of initialize the adjoint solve, and then we do the optimization. And so hopefully this should work. So this is an adjoint. That's the adjoint equation, which it's hard to give an interpretation to what that actually means, but this is the forward solve. So it's doing forward solve. Okay, accepted the step size, doing the line search that does the next adjoint because it's computing the gradient. Does another forward solve, and eventually we'll accept step size. Does another adjoint, compute the gradient, etc., etc. And okay, there's a lot of output there. All right, so let me start to conclude. So this might be helpful for some people. If you're doing time-dependent simulations, especially if you want to do optimal control, you have to do multiple forward and back solves. If you do the typical, VTK stuff, they want you to do PVD format, which saves all the time steps in separate files, and each one has the mesh repeated over and over again. So it's quite expensive. So I have a package. It's on GitHub, VTK write. So this avoids that problem. So I'll just quit. So it's XML format. Writes the mesh once for all the time steps, and then I store these. This is just the components of Q. Like that's the 0, 0 entry, and then for each time step, 0, 1, 2, and then it stores the off diagonal, and then the lower, and then eventually it's everything stored in raw format. So that's more efficient than doing the typical PVD thing. So. All right, so that's basically it. One extension, do cholesteric shells. Energy looks a little different. You got the curl of Q, but this could be written in the form that I showed before. And so this is what a simulation looks like. I apologize, this is actually done in FireDrick, but it could obviously be done in ngSolve as well. So I'll stop there.
Whatever GitHub package you want to share, people are interested.
Yeah. If anyone, just let me know.
Please.
What are you solving exactly? So what are you talking there?
So this is the elastic energy, and you have like either a homeotropic or a planar anchoring, depending on the setting, and you're doing energy minimization again, right?
What are you plotting in the
Yes, what am I plotting? So this is so you take the dominant eigenvector again of the Q, and then you dot that with the radial vector, basically with the normal vector of the surface there.
the magnetic field, what you're seeing there somehow.
Yeah. So for example, the director is say pointing out here, but then twists at the blue, and then it just keeps.
It's super interesting, but that's it.
Yeah, we're out of time. So.
And now we are perfect in time for coffee break. Every stop there. talk, we have 4 long-time NGSolve experts. Starting is Jay on space-time methods using 10 pitching methods.
All right. Did you all have enough of me yesterday? I forgot to start the screen recording. Just give me 1 second. Okay, so this talk is about this software, an add-on to NGSolve, available in GitHub. If you Google NGS10s, it'll come up, or here's the address. You can clone it if you like. The story of this is that a couple of years, I don't remember exactly how many years, before the pandemic, Joachim was sitting 2 blocks down in a glorious summer like today, and started this code. And a lot of people then made contributions to this. Paul Stoker, who's here, has made contributions. Dow Drake, who's here, has made contributions. And bulk of contributions came from a student of Joachim, Christoph Wintersteiger. Okay, so this is a C++ extension of NGSolve with a Python interface. There should be a pip installer now, as of yesterday, maybe. It's working, we think. But otherwise, you can certainly build it. You know, if you have an NGSolve build, you can. Okay, so inside the documentation folder, you'll find 2 tutorials, and my plan is to run through them in high-speed mode. Okay, so before we talk about what we can do about the software, we need to agree on a language. I think, is it too small, or? Yeah? Is that better? That's better. Right, okay. So the first term we need to know is the causality condition. And I'm going to argue that tens are very natural for solving hyperbolic problems. And this is not a new statement. In fact, much of what I know about tens came from a paper of Peter Monk and Richter that I read a couple of years ago. And there is this notion of causality condition, which is easy to describe using this picture. If you have a hyperbolic problem, you have finite speed of propagation. So if you pitch a tent in space-time, you have initial data given here, and you'll be able to solve on this tent if the tent pole height is not too high. If the tent pole height is very high, like this, then the domain of dependence of a point in the tent falls outside the tent, and therefore you don't have enough data to solve at that point. So this notion of constraining the height of this tent-shaped region is known as the causality condition. It depends on the wave speed. So NGS10's package provides facilities to mesh a space-time region using tent objects like what you saw before, and then a space-time slab is filled up with tents, and then you can do this process of solving tent by tent a hyperbolic problem. Okay, so let's import NGSolve, and we import from NGS10's this object called tent slab. Okay, and it's easy to see it in a picture. If I have a one-dimensional mesh, I will see a picture of a tent slab after pitching tents. So I've just now created a tent slab object, and here is the time height of the tent slab, and here's an estimate of the maximal wave speed that we have to input to the tent slab so as to constrain the heights of the tent pole. And then we say pitch tents, and then you'll see a picture like this of the tents. This is the time direction, this is the space direction, and you see the blue level tents form the first advancing front, and on top of it, you have tents like this. So this is a tent that's pitched, I don't know, in a valley, so there's the green level front is the next advancing front, and so forth.
Jay?
Yep.
Which type of Cs do you accept? Can you go up to whatever?
C?
Yeah.
Number?
Is it complete function or just a number?
Number.
Okay.
Number.
Oh, coefficient function also works.
Oh, good. Okay, there we go. For all the examples in that I've prepared, this is an overestimate of the speed. But when in cases like in nonlinear hyperbolic systems where the wave speed changes, conceivably you could use a coefficient function. Okay, so now one thing I want to point out right away is that if you look at these blue tents, you see that you can process this in parallel, and this in parallel, and the other blue tent in parallel. And once you've solved the blue tents, then you can solve the green ones in parallel, and then the red ones in parallel. So there is a natural parallelism here, but you have to keep track of the dependencies of the levels, and for that we create a directed acyclic graph. This does not correspond to the picture there, but here are the tents that can be processed in parallel first, and then once this is done, these can be processed in parallel, and then further tents that depend on it. So this is implemented using a concurrent queue where the threads are waiting for tasks, and when a tent is ready, it goes in and gets processed. Okay, and there are various query routines. We won't go into the details of that. But to make things interesting, you need a non-uniform mesh. So the reason for using tents is not for meshes like the one you saw, but if you have a spatial mesh that is not uniform, like here, then you see that you have, using tents, you have automatically achieved local time stepping or variable time stepping. So at this point, where the spatial mesh size is small, you see you're taking many time steps. You think of these heights as time steps, whereas here you're taking fewer time steps, and there is a natural variation from the high time step region to the low time step region, and this is independent of what you do inside. You might have a high order discretization in space and time, but it doesn't matter. You can do this tent marching together with the automatic local time stepping. Okay, so let's solve a problem, an acoustic wave in two space dimensions. The package is set up to receive first order hyperbolic equations or first order conservation laws. So here's a wave equation in the textbook form, in the second order form. The first thing to do is to convert it into a first order conservation law. We introduce the flux, that's the Q, and another scalar variable, and here is now the state vector for this hyperbolic system. It's derived from this equation. If you solve this, you're essentially solving the acoustic wave equation. Okay, just to not have the unit square, we have a domain that looks like this. It's got tiny elements here and bigger elements up there, right? And we're injecting a wave here, and it opens up into a larger domain. And what is pictured here is the initial solution, and we have to propagate this initial solution using the wave equation. Okay, so we pitch tents on this domain using a somewhat conservative tent height, and we can see the pitched tents. This is the first layer of tents. You can rotate this, and you see the first layer of tents, and you can change that argument, and then you will see the higher level tents. And there's some facilities to color the tents, but maybe if you're a fan of ParaView, then you could send it to ParaView. I see that Sean is a fan of ParaView, so you could send it into a VTK file and then view it there. Now the next item we need in order to solve this wave problem is this wave module from the conservation law. So we import the wave module, and then we make an object of the wave class with boundary conditions and so forth, and we provide it with a grid function on the spatial domain, which the initial function is the one you saw, and then we have to set a solver. Okay, so now we've made the object. Now we're going to set the solver. But at this point, maybe I should tell you, I'm talking about setting a solver using a spatial discretization and some sort of time stepping, but really we're talking about tens, which is not a tensor product domain. So you have every right to ask me, what are you talking about? This is a space-time domain. What does it mean to say a spatial discretization? What does it mean to say time stepping within a space-time domain? Let me sidestep those questions because that's in this next tutorial. If I get there, we'll talk about it. But for the moment, we'll proceed to set an explicit time stepping within a tent. And what it's doing is it's taking a tent, it's splitting a tent into subtents, and then propagating solutions on the bottom to this to the top of the first subtent and the next subtent, and so on. And the reason we need to do that is explicit schemes are, in order to make them stable, you need to have a sort of a discrete CFL-like condition, and this is the analog of the discrete CFL condition. Split the tent into subtents, sufficiently many subtents, so you get stability. So in this case, we've split the subtent in every tent into 10 subtents, and we've set the default tent solver, which is something called a structure-aware Runge-Kutta time stepping combined with a DG spatial discretization. Okay, we're ready to solve, almost. This is the solve routine. What it does is, one call of this will take data from the bottom of the 10 slab, propagate it through the tens, and get you the solution at the top of the 10 slab. Okay, it went by too fast. It already solved, but I've saved the solution here, and you can sort of see what's happening. So we're only plotting the solution at the top of the 10 slabs. Right, so we're not looking at the solution in the in-between tens, and you see the wave spreading out. Okay, so what we've seen is these words that are important to understand is the 10 business, the causality condition, this advancing space-time fronts in blue and green and so forth, and the 10 slab object that's coded in NGS tens. And we can march through the tens in parallel. We can do also not only tent marching, but also explicit time marching within tens using, and you can ensure stability by making sufficiently many subtens. And we've seen how to solve an acoustic wave equation. And I have a few more minutes to show you the next tutorial, which is about some of the intrinsics of what is happening. How do you set the spatial discretization in a space-time domain, and what does it mean to say time step through a tent and so forth. For that, you need this notion of maps. You have to map a tent into a tensor product domain where it then becomes feasible to talk about time stepping and spatial discretization. Okay, so the idea is very simple in a picture. Here's the tent, here's the tensor product domain, and there's a mapping. And the mapping is simple enough to write down right there. This mapping is a degenerate mapping. These two-dimensional faces have gone into one-dimensional edges. And if phi bod, and phi bod is if the bottom of the tent is a graph of this piecewise linear function, and the top of the tent is the graph of this piecewise linear function, then the mapping is simply described using these little phis and capital phis. And then there is this fact. If you want to solve this hyperbolic system on the physical tent, then it's enough to solve it in the tensor product domain if the pullback of the hyperbolic solution satisfies this strange equation. This is the standard hyperbolic equation that everybody's familiar with. What has happened is that you have a d over d mapped time of something that looks like a time-dependent mass term together with the delta that depends on tent geometry. The phi and the delta depends on tent geometry. Okay, so the equation has become complicated, but we know what the equation is, and here we can do spatial discretization and temporal time stepping, and that's what we do when we set these solvers inside the tent. We're saying we're going to do dg in order to handle this term, and we're going to do a specialized time stepping called this structure-aware Runge-Kutta time steps for handling the d over d tau. Tau, we call tau the pseudo time because it's not the real time. This is t is the real time. Okay, so if you want to specify that instead of just importing a ready-made module, sorry, Sean.
You said the mapping was generative.
Yeah.
That doesn't mess anything up?
Well, it creates things like this, which is yeah, that's the sign of messing up that you see. And this delta is a degenerate way. It's a piecewise linear function that vanishes on the boundary, and you don't want to take one of delta. Okay, so previously we just imported a ready-made module called the wave submodule and then asked it to solve. If you want to solve your own hyperbolic equations, then you have to do a little bit more work. But you can do that work in Python, and you can do so by specifying what problem you want to solve. Meaning, what is this f? Because the f determines your hyperbolic problem. So you have to specify the hyperbolic problem, and you have to do so using a function. And you can do so in a Python function. You say, here is my hyperbolic flux, little f, as a function of u. And you have to say the discretization. Now, the discretization implemented is the DG discretization. There are, everybody has their own favorite DG discretizations. But they all look like this. You integrate by parts, the divergence became the gradient, and the boundary terms have this form, a numerical flux multiplied by something. Whatever flux you want, you put in there. And you put in there through another function. So you declare a Python function numerical flux based on the values on a facet. There are two values, u minus and u plus of the DG function. So imagine that you're given as input u minus and u plus from somewhere, and then you write the expression for the numerical flux on that facet, and you write the expression for the numerical flux on the boundary, okay? And then there's one non-standard ingredient based on the tent geometry. And that's coming from this term. If you call this term y, you have to provide a function that extracts u from y. So solve this equation. Often you can solve this by hand. So you get that expression and put that into this function called inverse map, and then you can solve a general problem. So here is an example of a linear advection, the simplest problem you can solve, I guess. We start with simple data like this. We've already pitched tens, and then we've defined all of these 4 required functions. And once you declare these functions, you provide that as input to an object called conservation law. Here's the conservation law constructor. You provide that as input, and you're ready to solve. Okay, did that go by too fast? Let me try that again. It's going to go by too fast again. Okay, there we go. Okay, you see the advection. Okay, so that's for a linear hyperbolic system. For a non-linear hyperbolic system, you have to play some more games because there's always 100 million shock capturing schemes, and we have implemented one from a paper of Germán, Pescetti, and Popov. And their idea is to use an entropy viscosity regularization. So you have to provide one definition of entropy and an entropy flux. The idea is that if you have a smooth solution, then you have conservation of entropy. But if you have a shock, then instead of this being an equality, that becomes an inequality. And you can sort of measure places where you have a residue, an entropy residue, where you don't have this equality, but you see signs of not equality, and they suggest right there should be where you put smoothing or artificial viscosity. So that means you have to provide entropy flux, and how you want to add the viscosity. Okay, all of that you can provide in Python using another 4 functions. Define your entropy function, its corresponding flux, and a DG discretization of the entropy conservation equation would have a numerical entropy flux, and define that, and then how you want the viscosity coefficient to be implemented, depending on the entropy residual that will be calculated and given to you as input. So as a user, we put all of these together, and with pitch tens, we define the 8 functions. Now we have 8 Python functions that we have to define, and those 8 functions go into the conservation law. Don't have too much time, so let me. Here are the 8 functions as input to the same conservation law object, and then we solve. I think we're pretty much ready to solve here. Okay, and I'm saving the solution, so if it goes by too fast, we can see it. Okay, here's a solution to the Burgers equation. It wants to crash, but it's trying. It's just the way. It's the way about to crash, but and you can see that again on a uniform scale. Oh, that is too slow. Okay. You're kidding me? There's a place to increase speed?
Yes, Martin. Now speed, there's speed. Yes.
Oh, okay. Thank you for telling me that. Okay, and it's interesting to look at the entropy residual to know where are the locations where artificial viscosity was added, and I've saved that too during the course of the simulation, and it's interesting to look at both. You see where these are regions of sharper transitions, and that's exactly where the entropy conservation law is being violated, and that's why we put in this artificial viscosity. All right, so that's all I have. Thank you very much. I think you're next. Okay, question. Sorry, Peter. Yes.
Do you have tutorial? Do you have tutorial for the system case? Do you have tutorial for the system case? The equation?
Yeah, there are some Python script, not tutorial, but some Python files that should work. It's in the demo folder.
You find on GitHub already, and
yeah,
you can try it. You can install and redesign it.
Peter?
Have you looked at moving domains?
Can you do a pullback of the domain?
Well, yeah, that would be one way. That would be, but then you get an anisotropic coefficients and so on.
That's not the problem.
That would complicate the template. Maybe
If the pullback equation is still can be guaranteed to be hyperbolic, then
I guess if it's not too big a change.
Yeah,
it's like a vibrating.
Yeah.
A vibrating transducer produces that, so it wouldn't move very much. If it moves too much, then you're then you're in trouble.
Yeah, we're within 1 time step. It's not moving too much. Right?
Yeah.
okay, that's yours. Okay, all yours.
Okay. Yeah, so I have the next add-on to ngSolve that I want to present. So this is a package that is called NGSXFAM. So you will see this is for amplitude discretizations. I prefer the term unfitted nowadays, but when I started this, I was more into XFAM, so that's why it's still that name, but okay. And a bit contrary to what Jay did and what we also saw in the other talks, I want to, similar more to what we saw for the curvature stuff, so I want to explain some features and also go a bit into details how they work. And if you're interested later on, we can really sit together in the hands-on and go through tutorials and examples in more detail. So first of all, I want to motivate which type of classes and numerical methods we are considering when we think about using NGS-XFAM. Then I want to discuss some main features of NGS-XFAM, so where it extends features of NGSolve, and then also at the end show some highlights where it's actually already used. So the considered problems that we consider are PDE problems, and they can be in the bulks or in the volume. It can be surface PDEs, it can be something coupled between two domains, interface problems, or even between surface and bulk. And then on top of that, so we also have typically the challenge and the kind of one of the main motivations that we have geometry and geometry evolution involved. So you have a domain, you have a moving domain, as Peter also was addressing just now. So so this can be physically because it's a moving domain, or you can also think about kind of a time of an optimization loop where you try to optimize something, the geometry for something else. Yeah? So this time of okay, and one of the main applications that I was also coming to the unfitted discretizations from is something moving domain type. So here you have a bubble heavily deforming during its rise process, and you have some concentration field evolving and dissoluting in that process. Okay, and this is kind of where you can motivate and decide if you want to do something fitted, body fitted, or unfitted. So for geometrically fitted situations, so that's what we typically saw and typically see and use so far. You can actually solve all those problems to some extent as well, but of course meshing and mesh tracking and especially remeshing can become a burden if you have really strong deformations, especially if you have topology changes on something close by, right? So the idea of geometrically unfitted discretizations is to decouple this, yeah? To say, okay, I want to have a computational mesh and I want to have a geometry, and these are more or less separated to have more flexibility. Now this comes with a few more challenges. Yeah, so all the nice things that you know from file elements, essentially, you don't have directly available for unfitted discretizations. You have to kind of recover this by proper discretization tools and analysis tools and so on. Yeah, so you have shape regular cuts. You have to care about numerical integration on your physical domain because obviously not parameterized by the mesh anymore. You have to think about imposing boundary conditions, time integration, and things like that. Okay, and there are kind of methods doing this. So it's, the idea is typically that you have a background for an element space, so VHBG here, and then, for example, for CADFEM, what you do is essentially you take those functions, you restrict this either to the physical domain or sometimes more precisely to the active main domain, so the mesh, the part of the mesh that you need to cover the physical geometry. Then there's XFAM, so this is more the idea that you have the background space and then you enrich this. Yeah, so this is the function we have here. So you enrich, for example, by a discontinuous function in order to be able to approximate functions across an interface that are indeed discontinuous. Then there's something like called TraceFAM to do the same kind of for PDs on surfaces by restricting functions from the volume background space to the embedded surface that is independently described. Okay, and if you use these fine element spaces and want to still do unfitted discretizations, then there are techniques like Nietzsche's method that you use for imposing boundary conditions. You need to care about stability. You will have something called ghost penalty and fine element aggregation, perhaps. And for time stepping, you will have to do some clever way of extension based methods or space-time in order to do proper time stepping, because obviously, yeah, if you think about finite method of lines approach with just finite difference stencils is obviously not a good idea if you cross domain boundaries. Okay, so, and there are different names for these methods, yeah, so CutFem, XFem, TraceFem are obviously here. Something called XDG, unfitted DG, finite cell method, immersed final method, so they go under lots of different names, but essentially these kind of techniques are all in there to some extent. Okay, so what is NGS-XFAM in that context? So this is kind of trying to enable some of those tools for ngSolve. So it's a small C++ library on top of ngSolve. Obviously, it also has a Python interface, very similar to the ngSolve stuff. It's on GitHub. You can install this through pip. I also put already a comment in the user meeting group of the forum where you can find the slides, by the way, but also further kind of material like the links and so on. Okay, so I started with developing NGS-XFAM during my PhD thesis time, where I was working with a different fine element package for this two-flow stuff. At some point, I had to do some preconditioning and stuff, and I was used to ngSolve for other problems, but kind of for the local group, I still use the other package. But at some point, I had to kind of do the same methods now in ngSolve, and then started to develop this NGS-XFAM package, because everything was much easier once I started doing this more seriously. Okay, so there's a short paper on Journal of Open Source Software. There's lots of Jupyter tutorials. Some of them are already now in the ngSolve iTutorial setup. There are more Python demos as well. We have a minimal, let's say, API documentation as well. As I said, it's in the user meeting chat if you wanna look it up. Okay, so let's go through the main features that we have. So first we start with what ngSolve is already giving us. Yeah, we saw this yesterday, and you all know this by now. So we have lots of very interesting and very nice fine element spaces, and in ngSolve we have this nice convenience of writing down variation formulations with help of differential symbols. So this dx, ds, and whatnot. The whole assembly and static condensation, kind of these type of features, we don't have to reinvent. We have things like types of degrees of freedoms that can be helpful. For example, we can use something like an unused DOF as a kind of preliminary tool if we want to deactivate certain degrees of freedoms, for example. Yeah, we can use lots of different preconditioners, linear solvers. We have something nice we will see like mesh deformation, so we can really work with deformed meshes quite easily. We can do something like a feature that we didn't discuss so far, but we can actually restrict integration to a certain set of elements. So you can do dx and then define on elements equal to, and then you put in a bit array of elements there to just do the integration on something specific. You can also provide here this deformation flag to your differential symbol, and that will lead to the fact that you don't integrate on the element that is in the mesh, but on the kind of the deformed mesh under the deformation that you prescribe. Okay, and then we have, of course, lots of other nice features that we have so far. So what is coming on top with NGS-XFAM is a bit more than I have here, but these are, let's say, the main features. So we have tools to work on submeshes. Yeah, of course, obviously that's what we want to do to some extent. So if you have your background mesh, but your physical domain is only a part of it, you just want to go there, but you don't have, let's say, the domain description that we saw yesterday, because it's not described in the mesh, but separately. So we need kind of tools to work on submeshes. You need to take care about numerical integration. That's something that we want to do. You need to do something about stability for some methods at least. Yeah, I like space-time methods for doing time integration in that context, and also have some facilities for that. Okay, so let's start with working on submeshes. So assume you have a situation like here on this figure. You want to solve something inside this potato. Then what you can do, we do most of the things with level set based functions. So we have some level set function, coefficient function here. And what we do first is we interpolate this in a P1 function, so a piecewise linear function. We'll see this is kind of a good starting point, because it makes topology of the geometry description much easier. And now you can call something. We have an object called the cut information class, which stores the information about obviously the cut in the mesh. And then you can ask for elements which have certain properties, and we distinguish neg, pause, and interface. So parts that are in the negative level set domain, so completely inside the domain, positive completely outside, and interface are those that are cut by the level set. And then there are combined types, like for example, has-neg is something like negative or interface. So these are all the elements that are relevant to describe the physical domain. Okay, you can get those, and then here we'll have bit arrays of elements. So before we saw bit arrays of regions or bit arrays of DOFs. This is now a bit array of elements. And yeah, you can do something similar for facets, depending on the neighbor types, let's say. And then you can use this, for example, to restrict final elements to the submeshes. So here, for example, you can now take all the degrees of freedoms of a certain final element space, so from your background final element space, restrict this to a set of elements, and then take the corresponding DOFs, and with the compress that we already saw also, you can just restrict the final element space to these degrees of freedoms. Or if you want to do this rather element-based directly, you can also call the restrict wrapper. This is now coming from NG6 you can just restrict the final element space to a certain set of elements. As I said before, you can also do this for integrals, so you can integrate just on an active part of the mesh by prescribing this defined elements part. This will not yet take care of the cut integration, but at least will restrict the assembly or the integration symbols to these set of elements. Sometimes it's also nice if the bilinear form is restricted to a set of elements, a set of facets. So especially we will need, for some of the stabilizations, we will need the TG couplings that I also talked about yesterday, and they will be, can make things quite expensive, but we will only need them for a few elements for stabilization purposes. And with a restricted bilinear form, we can say on which element and in which facets we actually want to create or reserve non-zero entries for in the sparsity of the matrix. Okay, so then numerical integration. So we want to do something like an integration, for example, on the interior part of your level set domain, so on the negative part. Then you can do this and then just solve the following way. So you take a level set function, P1, so level set P1 function, and now here you have a new differential symbol now, dcut. You prescribe the level set function, you describe the domain, so which part of the level set domain you want to integrate on neg, pause, or interface, and then you can prescribe also the order of the integration. Okay, and what it does then is it exploits, and this is something that we exploit heavily, that we have a piecewise linear function, and if the level set function is a piecewise linear function, then the cut configurations are pretty limited and comparatively easy compared to the general case. Yeah, so for example, in the tetrahedra case, piecewise linear zero level will divide the tetrahedra into this prism and this tetrahedra, or into two prisms. We can do this subdivision and then do the integration on each of these parts separately. Now, so more easily here in 2D, you have a triangle, you have a linear cut, and then, for example, for integrating on this side, you can just apply a quadrature rule for the corresponding simplex here, or you subdivide this part into two and get other integration rules. So that's comparatively easy, and that's what you get essentially by this dcut thing here. Of course, we want to rather do higher order schemes, and if we use the piecewise linear reconstruction for the geometry only, then you are limited to second order accuracy. So what we can do to improve on that is that we apply a mesh deformation. Yeah, so similar to what you might know from isoparametric approximation of your boundaries, you can do the same trick for interior geometries. Now here with the piecewise linear reconstruction of your interface, but you actually have more information. That's the assumption. You have more information about the true level set function. Then you can construct a mapping that deforms your mesh such that it kind of is close to your true geometry. And it's also just a local deformation, so a squared maximum. It's also local, so it's like really like in the isoparametric boundary approximation case. For that, we have this submodule level set curving, the level set mesh adaptation class, which you can then call the calc deformation. So the class will have a P1 reference configuration. It computes the improved, or the mapping that gives us the improvement, and then based on those, you can now call the integration routine again. So the only change compared to the last slide is that you now describe the deformation, which is standard NG-solve feature on top here. Yeah, so essentially, this is exactly reflecting the fact that you do the integration here plus the deformation to the improved, let's say, geometry approximation case. So I skipped another feature. So you can also describe some geometries which are described by multiple level set functions. Yeah, because this will work for smooth domains. But if you have something non-smooth with corners and so on, you might rather want to describe something by multiple level sets. You can also do this in ngSolve. But then let's say the topology of describing these domains is more complicated, and I kind of skipped this here. You can find this, for example, in the backup slides if you're interested, or we can discuss this later on. Let me come to stability. So for stability, one standard trick in unfitted final elements is that if you have an element that is bad cut, or which is cut at all, in order to get stability, you want to borrow stability typically from the neighbor. And one thing to do this is called a ghost penalty. And for that, we offer such a term here, which is an integral over a facet patch. So we have a facet close by or directly aligned to one of these problematic elements. And then what you have here is an integral over the facet patch. And this is kind of what is new now in ngSolve, essentially with the XFAM package. You have an integral over the element patch. And what you integrate now is the volumetric jump of your function u. So this is evaluating the function on the one element as a polynomial and subtracting the other, the neighboring element as a polynomial, both polynomials in RD, and subtracting essentially the difference of those two polynomials. So essentially the kernel of this guy is just the patchwise polynomial. Okay, so this is essentially a smoothing type stabilization term, and you can get this type of integration symbol with the d-facet patch in ngSolve. So we also have something I would call stability patches. So the region where you need to add stabilization is always kind of local, and we can form stability patches that make sure that in each of the patches that we form, every cut element or every bad element that might be bad cut is connected to one element in the interior, one root element, so that we form these set of patches. And if we have these patches, then you can do several things. So this is here the idea of the element aggregation object. So you get two types of bit arrays for negative, so for the good elements and then the bad elements. You put this into the element aggregation class, and what you kind of get from this is these form patches. And now on these patches, you can do things like you can restrict the stabilizations, for example, ghost penalty, to act only interior to this facets. You can also solve local problems with a patchwise solve. That might be convenient or necessary sometimes if you just have information on the physical domain, but you need this on the active mesh or things like that, or you want to do some type of post-processing on your data. And what you can also do is kind of do a final element extension. So this is what we have here with this aggregated embedding. So the idea there is that you discard degrees of freedoms that are only in the problematic domain, so which don't have a good support in the physical domain. You discard them completely and just kind of constrain them to be kind of an extension of the interior degrees of freedoms. Then the idea would be that you assemble the problem first without caring about good or bad cuts, and then later on kind of imposing this embedding matrix, this kind of matrix that maps from the restricted domain, so from the interior, to the degrees of freedoms from the whole domain. And then essentially what you have here is E transpose A E, so a smaller matrix that you can inverse. You can embed this back and then kind of solve the problem with well-conditioned and so on using this kind of trick. Okay, so finally, the last kind of feature that I want to discuss is space-time file elements. So here the motivation is of course moving domains with this level set geometry, but here's kind of just the simplest slide for the fitted situation. Because this already kind of gives us some new features that you can see here. So if you want to solve a space-time problem, for example, heat equation, what we offer now is kind of that you have a tensor product space on each time slab. So this is tensor product discretizations, and this here you describe essentially by a polynomial in time, so the scalar time file element, which is essentially more or less just the standard segment segment file element from NGSolve. And then you can take a tensor product here with the standard background finite element space in space. And then you have a space-time finite element. So the grid function, everything is standard. You have a new differential symbol here for now integration in space and time. So we have integration rules essentially now in space and time acting here. We do everything with respect to the reference, let's say, time slab. So this is domain, spatial domain times the reference interval 0, 1. So that's why on the user level you have to kind of transform the delta t terms in your integral and your differential operators. Yeah, we also have the time derivative operator here, dtref. Yeah, so that's a time derivative operator on the reference interval. Yeah, and then you have essentially what you need for the space-time formulation with upwinding in time in space-time dg. So we have time derivative of u times v plus gradient u gradient v in the space-time cylinder plus uv, and then here you have the spatial integral only with reference time 0, so that means you have the bottom of your time slab where you integrate. And then the same for the right-hand side, to impose essentially the initial conditions on that domain and the source term in the space-time. Okay, so I will skip essentially the corresponding thing. So here is essentially what I'll skip. You can do the same for the space-time unfitted situation where we have a level set then in space-time. You can integrate on this space-time level set and so on. This is getting a bit more complex, of course, and I will skip this here. Just briefly saying that the idea of this isoparametric mapping in space-time, and also to get higher order accuracy, also works in that setting. It's also implemented, and it's also quite conveniently obtainable on the Python level. Okay, so with that, I just kind of coming towards the end. So we already have a few papers. So this is now a list of papers that use NGS-XFAM already. You will of course see lots of names from my group, but also several others doing cool things with that. So we have lots of fictitious domain applications. We also have traps, as you will see in a minute. Interface problems, Stokes or Scalar. Gusheng did something with fractured porous media using NGS-XFAM. He also did something using space-time for the fitted, so exactly what I had on the slide before. Yeah, we obviously do something with moving domains with space-time. Also do something with moving domains with time stepping. We also have something fluid structure interaction and with unfitted discretizations. And there are people doing surface PDEs and model order reduction with NGS-XFAM. Okay, so with that, thank you for your attention, and if you're interested, we can do more.
If you have to do this all tomorrow.
Yes. Good. Questions? Then. What is it? Control. Full screen shortcuts? What? Command L. Okay, Command L.
Oh yeah, there we go. Okay, thanks. Yes, I will talk about another add-on to NGSolve, which is NGS-Trefts, an add-on to implement Trefts methods. So, of course, I will start by introducing Trefts methods to you and some different flavors of Trefts methods that we have implemented in NGSolve. So this will be the first part of my talk on Trefts DG, discontinuous Galerkin methods. The main idea always being that we have a DG scheme and we are using special functions, Trefts functions, to reduce the degrees of freedom in this DG scheme. Okay? And then in the second part of my talk, I will talk about Trefts methods together with NGS-10. So this is the package that Jay just presented. So we can do 10 pitching with Trefts functions and then also Trefts methods on unfitted geometries. So combined with NGS-XFAM, which is the package that Christoph just talked about. Okay, so a short introduction to the package. I started working on this in the beginning of my PhD in 2018. It's of course an open source code that you can find on GitHub, and you can install it via pip on Linux and Mac. And I should also mention, so in my PhD in the beginning, the focus was on methods for the acoustic wave equation. So you will see a lot of the methods have a slight focus on acoustic wave equations, while so especially during my postdoc now with Christoph, we generalized this tool to a bunch of more equations, which you will see. All right, so let me start with the introduction to the Treft spaces and the Treft CG method in ngSolve. So what is the idea of Treft methods? I already said this. We start with a DG scheme, your favorite DG method in ngSolve, and instead of using full polynomial spaces, we want to use the Treft spaces as test and trial functions. The Treft spaces on each element. So again, we have a DG scheme, so the basis functions decouple onto each element, right? And on each element, we use functions that lie in the kernel of the operator to approximate our solution. So here I'm writing the functions that vanish on the operator L for our PDE given with the operator L, right? This will greatly reduce the number of degrees of freedom that we are using compared to the full polynomial space. However, a few caveats that you can already see on the slide. So first of all, in order for this space to have the good approximation properties as the full polynomial space, originally, so one would need something like constant coefficients in the operator. So this is a theme that will continue throughout the talk, and we will also see some methods to mitigate this. And also, this space only is a good approximation for solutions to the homogeneous problem, so without the source term on the right-hand side, which we'll also challenge later on. One should also mention for several time harmonic problems, so like Helmholtz or time harmonic Maxwell, this space is not the correct Treft space is not a polynomial space, but instead a space of plane wave functions. Yeah, so yeah, this will also pop up later in the talk. Okay, so just an example to exemplify this for the Laplace equation here. The Treft space, of course, would be the space of harmonic polynomials in this case. And your DG scheme could be your the standard symmetric interior penalty DG scheme. And then, so using this together with our Treft space, we have the Treft CG method. So the DG handles all the H1, so the jumps and averages across faces in order to give us, in the end, yeah, some weak continuity in the method. And on each element, we can choose our basis functions as we like, and these are the Treft functions. Okay, how does this look in Python? Once we import our package ngS Trefts, instead of using the L2 space, which we would usually use to construct use the DG methods, we simply use the Trefts FA space. We pass, as always, the mesh, the order, and then the Treft space, of course, needs to know with respect to which operator it is supposed to be a Treft. Here we can use Laplace to get harmonic polynomials. Helmholtz would use the plane waves. Wave for the acoustic wave equation, so Treft functions with respect to the acoustic wave equation. Yeah, so these are the ones that are currently implemented. And of course, the DG jumps would always be set to true in order to use it with the DG formulation. How does this work under the hood? So what do we have to take care of on the C++ side? Here, one has to be aware that a mapping from a reference element is difficult or not easily possible for the Treft functions, since if you scale your element, so you stretch your element in a strange way, then you would ruin the Treft's property. So instead we are using a scalar mapped element, which evaluates our basis functions directly on the physical element in ngSolve. Okay, now the next part of my talk, so now that we've seen the Treft spaces, I want to talk about a generalization, which is the quasi-Trefts method, which we have done for the acoustic wave equation. Here we are tackling the issue of non-constant coefficients. So looking at the acoustic wave equation with non-constant coefficients, we can also do a type of Trefts method. And in order to generalize the Trefts method, we need to alter the condition in our Treft space. The main idea here is instead of requiring that our operator applied to our basis functions vanishes, we need to relax this condition, and we do this by requiring that the Taylor polynomial of the operator applied to our basis functions vanishes, or equivalently, all the derivatives evaluated in the center point of the element vanish. This idea gives us the quasi-Treft space, and this is a viable condition in order to again construct by hand these basis functions, these Treft spaces functions, which we can then use in ngSolve. Yeah. Come again? The G is the wave speed, the varying wave speed, depending on is the coefficient. Yeah. And yes, so we assume it's smoothly varying. Okay. Yes.
I was wondering why does infinite summation?
We just need a Taylor expansion, so it's a smooth coefficient. Yes. We require this to build the Treft functions. Yes.
So xk is the center of.
Exactly, it's the center of the element. Yeah. Okay. Yes. Again, this works in Python. We get our Trefts FA space in a similar way. This time we ask for a quasi-Trefts space for the wave equation. We set the coefficient, and here you can see some nice pictures with so the wave speed starting from the bottom to the top is increasing, so the wave moves faster on the top. Okay, so this was one of the ideas to generalize this Trefts approach for more complicated operators. Now I want to talk about the embedded Trefts method, which is a tool to generalize this even further. Here the main idea is that we do not want to construct the basis functions by hand anymore. So instead of computing these basis functions by hand, we want to use an embedding. An embedding from the standard polynomial space, the standard DG basis. So we want to embed our Treft basis functions into the standard DG basis using the embedding matrix capital T here. If we can find such an embedding, then instead of solving the full DG system, capital A here, we simply project onto the Treft subspace and then use again the much smaller Trefts DG formulation of TAT here. Now the main idea of the embedded Trefts method is the construction of this embedding matrix. The embedding matrix you can simply get by computing the kernel of this matrix W here. So on each element we want, of course, that the operator applied to our basis function vanishes, which is equivalent to finding the kernel of this matrix. So you have to notice that this is, of course, a element-wise operation. So we can do this on each element. These are small matrices. And we can do this in parallel. And yeah, we do this using singular value decomposition, for example, or QR. So we can find the kernel, and this immediately gives us the embedding, which will be a block diagonal matrix, which we can then apply to our matrix A of the DG scheme. So this not only allows us to easily implement Treft's DG functions, but we can also challenge one of the issues I talked about in the beginning. So what about non-homogeneous problems? If we have now a non-homogeneous problem, while we are computing our embedding, so again, if we do the SVD of these local matrices, we get the embedding from the zero singular values. But we also have available to us the non-zero part, and this we can use to construct local particular solutions, right? So the red part will be our Treft embedding, which I talked about in the previous slide, and then we can also construct a particular element-wise particular solutions, which we can use to homogenize the system. Then we can solve the homogenized system with our Treft functions. Yeah, so generalizing this to inhomogeneous problems. Another thing that we can do is we can find an embedding also for operators with varying coefficients, or operators like the Helmholtz operator that classically does not have a polynomial Treft space. This we do by, again, relaxing the condition on a Treft space. So previously we relaxed the condition by using the Taylor polynomial. This time we can write something even more general. Now we simply want that the operator of these functions under some projection vanishes. Here we use the projection onto a smaller polynomial space of a smaller order. So as you can see here, we generalize this. So we take some subsets. So for example, if V is the full polynomial space over the P, and we have some Laplacian with the coefficient inside, then we would use, we would project onto the polynomials of order P minus 2. Of course, for the standard Laplacian, this is equivalent then to use our previous method with the L applied to the full polynomials. Okay, this way we can again construct such an embedding matrix using this embedded Trefts method for operators like Helmholtz or varying coefficients. So how does this look in Python in ngSolve? Here we have so the general idea of the scheme. We have our DG system given by our matrix, our linear system given by matrix A and the right-hand side L. We do what I just described. We compute the kernel element-wise locally of this matrix W, and then we use this embedding. So in green you can see the embedded Trefts method, and in red is the additional part for homogenizing the system. And then we solve this reduced system. On the Python side, we have the function Trefts embedding, which you pass the finite element space, the two finite element space, the operator with respect to you want to construct the embedding with, and then also if you want to homogenize, you pass the right-hand side, which will then give you this element-wise particular solution. Yeah, so this is how you do it in ngSolve. All right. Here are some numerical examples. For the bus problem, we are comparing the full polynomial space to the harmonic polynomial Trefts space and also the embedded Trefts method. We can see optimal convergence rates of all the three methods for different polynomial degree. And on the right-hand side, you have some timings. So here are the timings for the polynomial space, embedded Trefts method and Trefts method, and we are comparing the different steps in the method. So the assembly of the linear system. In case of the embedded Trefts method, we have to do this element-wise singular value decomposition, which is in orange, and the solver step. You can see the largest part of the time is spent on solving the system. The system for the Trefts methods is much smaller than for the full polynomial space, so we have some nice times here. And in orange, you can see this element-wise singular value decomposition barely takes up any time, even compared to the assembly step. It's vanishingly small. Okay, so these were the three flavors of Trefts methods that we currently have in ngSolve. Now I want to briefly talk about the combination with NGS-TENS and then with NGS-ESFEM. So you already heard from Jay, the main idea of NGS-TENS is to construct these 10-pitched meshes in space and time. You've already seen this part of the code. So once we have constructed such a TENS lab, in ngSolve, we can pass it to a similar function from NGS-Trefts, not called wave, but T-wave, and this will solve the acoustic wave equation using Trefts functions. So the main idea again, here we simply use a space-time method on each of the TENS, a space-time formulation. We can solve using the input from the bottom of the tent and evolve to the top, so there's no mapping to a tensor product shape going on here. We immediately solve on each of these TENS using a Trefts DG formulation. Yeah, and so here's the code. The syntax is very similar to NGS-TENS. Okay, and last but not least, the combination with unfitted methods. So here, Trefts methods pair very naturally with the idea of unfitted methods. So once you have a DG formulation on an unfitted geometry, you already have seen the idea. So we have a geometry that is not fitted to a mesh, but instead given by a level set function. We can again use in ngSolve simply the restriction of our spaces to this geometry. Again, we can also do this with the Trefts finite element space. And you have already heard that one of the main challenges of these unfitted methods is the stabilization with respect to small cuts. So if we have the geometry cutting one of our elements in a way that it is not shape regular anymore, so it produces very small or thin elements, then we need to stabilize the method. And the good news is that Trefts methods work very naturally with the two major kinds of stabilization that are out there. So either one can use element aggregation where for a badly cut element, we simply glue it to one of the elements in the interior domain and produce like a macro element. So Drafts methods are not dependent on the number of facets or anything, so it easily works on a polygonal shaped domain like these aggregated elements. And for the ghost penalty stabilization, which couples two adjacent elements with this penalization term in order to stabilize the method, also works well with the Drafts DG formulation. All right, so we have online the full documentation of the NGS Drafts package and a bunch of notebooks you can check out tomorrow and play around with. And finally, here are so some papers, the papers using the package, and a link to the GitHub and the documentation. Okay, thanks.
Try out all this tomorrow, it's a minute tutorial. We are coming to Open Cascade Geometry Modeling by Christoph Verlagter.
Yeah, final talk of before lunch, a bit lighter. But since a lot has been done on this Open Cascade, you see it? What? On this Open Cascade interface in NetGen, and this is now the recommended way to model your geometries, we decided to also have some section on how to design in this new wrapper your geometries. And since Joachim and Jay focus so much on the unit square, we also have to do a little bit more complicated geometries now. I also want to emphasize, I will now more focus on like some neat tricks that I find why it's good to switch to Open Cascade, and we will tomorrow in the workshops have more about like 3D modeling and more fancy geometries, and now I will focus on like how to prescribe the boundaries and stuff like that quite easily. So I will start with 2D. In 2D, we basically sketch the geometry in a work plane. So you use this work plane object, and then you can draw on it basically like circles, rectangles, and extrude the faces from this from that work plane. All of these objects in Open Cascade are always in 3D space. So we only say that we have a 2D geometry as soon as we transfer them to NetGen. In Open Cascade, everything is in 3D. Yeah, you can name shapes. Everything, a vertex, an edge, a face, a solid is a shape, and they have basically the same functions. So if you want to name your domains in 2D, you name the faces. So there's a bunch of different ways to combine shapes. One of them is compound. Compound creates kind of a collection of the faces without gluing them together and without merging them, so they are just like flying around. Even if they would overlap, they wouldn't be merged together in the geometry. So here I'm going a bit quick over that. We will look more into details there tomorrow. But here I just created some random objects. And then what you can do is you can move them around, you can copy them, you can rotate them, you can mirror them, stuff like that. And combine them with the second operator that we have to combine geometries is the glue operator, which glues them together but doesn't merge interfaces. So it will be kept as separate domains. Of course, they should touch each other, but they will have a common interface in between them. One important thing to note is that all the operations in NetGen create copies of the domain. So if you do something like t.move, it doesn't actually move t, but it gives you back a copy of the moved object. The third operator, or actually the second operator in that tutorial, is the sum operator, which would really merge the two geometries. So there will be no interface then in between. And in this small example, I already did a lot of things. So this right part here is with the sum operator, so it really is merged. There is no interface in between anymore. These two are glued together, so they will be kept separately, and their names are kept, as you see here. These two are compound together, so they actually don't have a common interface. And now the first trick that is not so well known, I think, is that, so you can, apart from giving them names, you can give them mesh sizes. So you can for each entity, you can say, on this edge I want to restrict the mesh size, on this vertex I want to restrict the mesh size. And if you pass to the compound these separate layers equals true, it will create for each object in this compound, so for the D1, for the D2, for the D3, and the move D3 and so on, it will generate a separate mesh tree. So mesh restrictions on D1 do not influence mesh restrictions on D3. One thing I missed, you can quite easily find some objects by requesting so for example, from this face, I want the nearest edge to this point, which will always select the one with its center closest to the point. So we only compare centers, we do not really compare the distance to the shape, as it would be too expensive. Yeah. I will push them actually to the main repo. In the tutorials? In the iTutorials. Yeah, and if there are any questions, you can interrupt me, because I think else later it will be too confusing to go back. Yeah.
Is it possible, you said that these are all 3D objects that you then pass to NetGen and they become 2D objects. Is it possible to have like a say for example a disk in the YZ plane that you pass to NetGen and it knows it's in the YZ plane, rather than having to, I mean, just say you want to solve a problem.
Yeah, if you want to, for example, say, solve a surface equation in the YZ plane,
yeah.
Yes, you can create you can actually, this work plane, wait, let's execute this cell. It has a constructor where you can actually give a local coordinate system, or actually you can give where the work plane is located in the global coordinate system. So you just give it axis.
Point, the normal vector, and direction of the local x-axis.
Yeah. So syntax would be something like, where do I have my work plane? Something like, then I don't know, center. What did you say? Y and local coordinate. So it's, yeah, this is the normal to the work plane, and then you have a local x direction.
Thank you.
Yeah, with this help, work plane is actually very helpful to like find all the possible things that you can draw in the work plane, like arcs, part of arcs, and so on. So as I said, NetGen only knows about the actual dimension, because you could also have like a surface equation on the plane XY plane. That's why you have to pass this dim equals 2 argument when you create a NetGen OCC geometry from the OCC shapes. And then we can mesh it, yeah, the usual way. And as you saw, because of these separate layers, the mesh size here is not influenced by the mesh size on the, so you really have non-conforming, non-matching meshes on this interface, and you can do local refinement without refining the other side. Yes, splines, like you can use, basically it uses internally this geom2d API interpolate. So you can also always look up the OCC geometry documentation with it, which is often a bit more detailed about what the arguments actually do. And it gets a list of points, then a flag for if it's already a closed spline, so if it's periodic, and optionally you can give some tangents to each point, in each point. And I think that Joachim has shown quite well, so I will skip the periodicity. Yeah.
Go back to the interface with the non-matching mesh.
Yes.
So now if I want to have a finite element space on the boundary on that interface.
Yeah.
Which side?
No, which side? So you can also, like, there will be two edges. So you can name, for example, you can say from this rectangle the bottom edge, so the minimum x, minimum y edge will be named my interface 1, and this edge you have to select somehow will be interface 2, and then you can define integrators on them. There is, for example, a good tutorial on that in the new tutorials, this Nietzsche method with the like moving mesh, where you do basically Nietzsche coupling on the two interfaces. Yeah, periodicity is done by this identify flag, so you identify one edge or a group of edges with another group of edges. And exactly, so the geometry, I will come to that a bit later in the 3D case. We can actually make it quite easily conforming as soon as the geometry somehow, by basically moving, so by basically ensuring that all the edges in 3D or in 2D, all the vertices are on both sides. One small thing to highlight is also this anisotropic mesh region generation interface, by specifying, also works the same way. You identify two edges, or in 3D two faces, but you just give a different identification type. It's in the naming is a bit, it's the naming from before, but you're also in 2D, so if you identify two edges, it's called closed surfaces, and it will then create it will basically create only an edge mesh on one side and copy it to the other side and fill it with quads, or in 3D with prisms. And then you can additionally afterwards call this crefine function with basically a list of slices, which is percentages where it has to cut. So if you zoom in here, there should be, with the touchpad it's a bit bad, but there should be also somewhere a small cut at 1% width. And this is quite a nice feature, for example, if you want to resolve some boundary layers effects.
Sorry, you say that, so it will be like symmetrical about an interface? Is that what you're saying? Like you could have this, if you had like say a disk, you know, and you have a circular interface embedded in the disk, and you want to have a mesh which is symmetric about that disk. Could you do it with this method?
Yeah.
Like a layer on each side of the, or on each side of the circle.
Yeah. So if you want to like have a one good application is like if you have like coatings or very thin layers on some structure, yes, you basically identify the inner layer with the outer layer, and you get a small. The only thing, the C refinement, you have to take care a little bit on curved surfaces. Yeah. It's a feature I want to add, but it's not yet in that the inner cuts are curved, so it might push through the elements yet, but might come in the next years. But you can always create multiple like geometry layers, and then you can curve. So it works with curving, but just the C-refine does not yet work with curving. Shouldn't be much.
If you do say geometric refinement towards the edge, then you inherit it from macro.
Yeah, if you put in many layers, you can do basically also a refined. It's just also it's basically a for loop, so it's also not that hard to. Well, then let's move to, or other questions for 2D geometries?
What's the version of OCC used?
It compiles, I think, against like from 7.5 to 7.7. I use the one provided by Arch, which is currently, I think, 7.7 something. I know that there is some smaller bugs in 7.5 and 7.6 why I upgraded, but it works. The most stuff that are not buggy in Open Cascade work. Okay. Yeah, then let's move to 3D. In 3D you can start also with the primitives that you know from CS geometries now. We wrap them basically almost or similar to before. The only thing is I think the autobrick is called now box. And the plane is called half space, but same arguments. And I mean, I don't know if there was an ellipsoid actually, but it's also available now. The ellipsoid, I don't know if it was in CSG. You also have the same operands as before. You have the multiplication with give the common, you have the plus which unifies, you have the glue as in 2D where the domains are kept separately. And you have some operators like extrusion and pipe and revolve to create from 2D sketches 3D objects. So yeah. There is nothing new, this is basically the same. Transformation we also saw already in 2D. The rotate is new, so you give it an axis and some angle in degrees and it rotates the object.
Capital X is actually a vector. You can say X plus CY to get the direction.
Yeah, and also a short note, there is this axis and axis. Axis gives you a coordinate system, or is a coordinate system where you give the normal vector and the local x coordinate. Axis is a point on the vector. Because at least I confused it in the beginning sometimes when I was wondering why my code doesn't work and you only see the small letter difference.
So if it follows the naming convention from the Open Cascade C++ interface, that they have the axis and X and D for the axis.
Yeah. Just try to simplify it as much as possible sometimes. Yeah, you can look at all the shapes. I copied it from Joachim's example. Basically that's what is inside of such an Open Cascade geometry. And as you see, you can access all from one solid. You can ask it for the faces, you can ask a face for the edges, but you always only can go down because the Open Cascade face does not yet know in which solid it has been glued into. So in Open Cascade, you can only go down. As soon as you put it into a netgen, as soon as you create a netgen mesh from it, you can also go up. So you can also ask a netgen face then, or actually an ngSolve face, which solids are adjacent to it. Looking as if I would do something. Yes.
So, can you define a tetrahedron as 4 half spaces?
Yeah, should work. I don't.
And it checks like for water tightness and all that.
It is watertight.
It is watertight by construction. So
this is not just the plane.
yeah.
The plane and everything on one side.
Sure.
And you have this axis, so the test is not an issue.
Right. It just seems like if you had lots of half spaces, you had some weird polyhedron, if they were to check,
Then you can get convex objects only. Open Cascade internally has a tolerance.
So what can happen is if you have like very close edges together, that it unifies them, but that's actually something we usually even want in because we don't want to mesh such small gaps. One thing that is still, but I hope to fix that in the next weeks because I already have something working, is that Open Cascade sometimes has like arbitrary edges. So for example, in a sphere, you get one edge from the parameterization of the coordinates of the local coordinate system, and you have that edge in the geometry. And of course, then you also get it in the mesh. So if you cut and combine multiple of these objects in a bad way, you would sometimes get bad constellations of these edge combinations, which can create some really bad meshes. So sometimes you, for example, have to rotate the sphere a little bit so that the edge is on the other side and it doesn't come close to the edge of the body that you're like cutting it with. But it might be that this is only a problem for the next month or so. Yeah, you can ask faces for its center of gravity. So the center always gives center of gravity. Like we query there also like Open Cascade functionality for that. You can ask an edge for its points. And what do we have here? Also, yeah, also like in face for the edges and so on. So these are the properties that you can set on basically all geometric entities. You can give them names, you can give them a mesh size, a local mesh size, you can give them a meshing layer. The meshing layer basically does the same that we had with these separate layers, so that the mesh size in one layer does not influence the mesh size in another layer. So you can differentiate with that, and you can give colors, so that is just for visualization, as far as I know, only for the faces right now. So now we come to the more interesting part, selection of faces. So when I create my geometry, how do I properly name boundary conditions? And there is some tricks where we're doing this section. So there is this min and max, which you give a vector, and it gives you the minimum face, also center of, also the face with the center in minimal direction of that vector. So you can here also combine like x plus 0.2 times y or something like that. Note one thing, it only gives you one of the faces there. So if there is multiple faces in the plane, so for example here, we also create another box, move it above it, and then actually we would want to have both of these faces there. It will only get one random ones that are in the same plane. But there is something that works in that case, and these are the selection operators. So you can also ask the solid for its faces, and then select only the ones that are where the center is larger or equal to 1. So the x coordinate of the center is larger or equal to 1. Yeah.
This larger and equal includes a tolerance also.
Yeah, so larger and equals compares for... I personally always put the tolerance in hard-coded because there we put a tolerance depending on the bounding box of the object, as far as I think. No. I like to compare always with like x greater than 1 minus, I don't know, 10 to the power of minus 6 or something, because then I have more control over it. But this also works.
Sorry, is this now referring to the center or bounding box?
It compares the center. So the center of the solid, the center of that should be in, for example, so here we have basically a unit, so 2 unit cubes. So this will give both the faces that are on the top unit cube and the bottom one, and then we can combine them multiple times, and it will always return a new list that we can actually use afterwards again. and yeah, also with namings and so on. And another option to select shapes of all kind is if you name them before somewhere else, and then you move them around, you cut and so on, and afterwards you can get it out again by just asking for the faces with that name. This list of shapes that are returned by these selection operators can also be combined. So you can, for example, ask for domains, so solids, with that name, their faces, and combine it with faces with that name. And you do you get the common subshapes by multiplying the two lists of shapes, and you get the union of the subshapes by adding them. And that's, from at least from my perspective, it was so these kind of syntaxes you will find in a lot of my codes, because it's very, very helpful to, for example, if you want to have the interfaces between two materials. So for example, I don't know, I have some metal and some oil, and I want all the boundaries between metal and oil to have some interface boundary conditions. So for example, some thermal dissipation coefficient. Then you can just select them like that and create a boundary name for it, for example. Don't know which cells I will later use, but I don't think this one. So periodic closed and closed surface identification work basically the same as in 2D, and I think this is also one example that we already had. The only pitfall, as you mentioned before already, is you have to have also periodic geometric entities. So for example, in that case, I constructed a box in a box, but the box touches the boundary at one side, as you see in the lower corner here. So here, of course, this left side, where the box is touching here, cannot be mapped to the other side. But there is a quite easy trick to fix that. So what I can do is I can ask for all the shapes in the left plane, get the edges out, glue them together. That's basically only because this transformation that I also use to identify the two faces needs to get one object in, but I glue them together, transform them to the other side, and glue them again into the shape. What I will get then is now a periodic shape. So now we have the box here in the corner, and here on the other side we have the two edges that we need to identify the two planes. And then we can do the periodic identification. And
actually, could you go back to the previous cell?
Mm-hmm.
I guess I'm just having trouble with how to read that.
So here you get
syntax.
So I ask the whole shape, the whole solid, for the faces in the left plane. Get the edges from them, glue them together to have one object, transform them to the other side.
Yeah, but how do you? It just says transform.
This I went too fast over that. This is basically the transformation from one side to the other side, so a translation that I also use in the periodic identification.
What type of expressions can I put there? Is it as flexible as coefficient functions, or?
No, it's linear affine transformations, and there's even a worse trick, because so it's also so basically it uses this GP-TRSF from Open Cascade, and there's one. There is like a GP-TRSF, so transformation, and the GP-G transformation. And if you want to make sure you use the G transformation, because it really is a linear affine transformation, the GP transformation is some optimization. So for example, non-isometric scaling so not in all coordinate direction the same, doesn't work in the GP transformation, and it actually doesn't even crash, so it just gives you a isometric one. So if you, I don't know, with the transformation, if you scale a sphere and you give like a non-isometric scaling, it will still create a sphere. You need to use the GPG transformation. Maybe I should add that here.
Can we are restricted to mapping OpenCascade provides? But we can say something else what the setup.
No further questions. So,
Good question. So, and also here, one thing I want to emphasize, so basically what this identify internally does is if you have only one face and one face on the other side, you can skip this transformation argument if and only if you have a translation. Then we automatically find the identification. If you have multiple faces or it's not a transformation, you need to give the transformation argument. And what it does is then basically it puts all these faces in the transformation and searches for matching faces on the other side and identifies them. So one also nice thing about that, which is not documented but a secret feature, is that this can also be more than what is, so more than the actual mapped two faces. So Joachim doesn't like that very much, but it's because he likes it to be bijective. But this works also. I can just take any faces and it will internally find the ones that this transformation maps to the other side. Yeah. So that was from the like tips and tricks tutorials for Open Cascade modeling. Shortly, I mean I'm already a bit over time, but shortly I can sketch what we will do tomorrow. So we'll just create some. The webgo did not close. Some Open Cascade tutorials where we will go over like a lot of the features, like for example how you can load in step files, combine them with your geometry, or cut something off a step file and produce, I don't know. Easiest example is for my application is like often you want to just compute on half the geometry, you get the geometry from a step file somewhere. So what you do is you load it in, you cut it with a half plane, and then you name the faces of the half. Yeah, we'll do stuff like that tomorrow if you're interested in these tutorials. If you have questions, feel free to come to me, and else have a good lunch now.
So that's it. Okay. Remember from the morning, Christopher, who is continue after lunch on getting into C++.
Yes, so I also want to give you a short and compact introduction into how to set up your own C++ extensions within NetGen or in ngSolve, whatever you want to extend. So, short overview about what we're talking in the next 15-20 minutes. Will be some short tips for building NetGen ngSolve from source. How to compile your Python module from either having a separate project to this compile Python module function. Then I will shortly introduce my little ngSolve. We'll go into more detail about that tomorrow in the hands-on sessions. I will show a little bit of concepts in ngSolve, mainly about how it is structured and how you find stuff in the source code. And then I will share a little bit of how to find bottlenecks in parallel, in the parallel code, like how to debug why your code is running so slow. Or one of the things that might be the reason for that. There's a multitude for that. First, I'm very happy because when I was setting up this talk, I, for the first time since a long time, tried to set up ngSolve with auto-completion and everything in different IDEs. And now finally one has arrived that manages all this submodule system that ngSolve builds quite well and easy. And it's in Visual Code, sadly. I don't use it, but for newcomers in C++ coding, I would really recommend it now, because it's basically two commands. You have to set up this .visualSetting JSON and specify one important thing is this CMake merged compile comments, and you give it some location, some file location where you want to store this merged compile comments. And in Windows, you need also to specify the CMake generator as Ninja, as far as I know, because only then these compile comments are actually generated. And what it does, it triggers a creation of some compiling information in different compile comments.json files. And the second command combines them into one file that the IDE understands, and so it knows with what flags it's compiled, like where your link locations are, and everything from go to definition to auto-completion and so on works quite well. And that's actually a huge improvement to starting with ngSolve, because then you can just right-click, go to definition, and find the files that you have to look into. And the second thing you have to set up is this C++ properties. I think you can also just press Ctrl-Shift-P and go to this edit configurations, and there somewhere you can specify the compile file. It's basically doing the same thing and filling in this compile comments. And basically what you do is you put in there the path that you selected before in this merged compile comments, and then Visual Code knows what to do and stuff. Like you can then, for example, I don't know, I hope it works now. When you demonstrate it live, it usually breaks then. But I don't know. Go to the bilinear form, you wonder what this slice matrix is actually about, and you can just go to definition and it will automatically jump to the right file and you can look at the implementation. You can also, I don't know, go back there and then do C dot and see what kind of functions.
This is not the auto-completion.
No. This is Copilot. And Copilot works for the stuff that is very popular, but not for ngSolve stuff. So you don't. But now, this is the real ngSolve stuff. No, but what I mean is for typical sorting algorithm, mainstream C++ coding, it works well. For ngSolve specific code, I wouldn't trust the Copilot. But for example, then if the auto-completion opens, this is really the ngSolve stuff that you have available as from a slice matrix, for example. And that can be very helpful if you start with that. So how can you start setting up your own C++ extension? I would recommend, there's now multiple ways to do that. I would still recommend setting up a separate project for that. One way is, for example, if you start with My Little ngSolve, which is basically a tutorial in starting C++ ngSolve, and copy the build structure from there. You can start out with that and then extend it and write your own functions into it. What you will need to know a bit about is first CMake. This is basically the compilation definition for your project, and PyBind 11, which is basically how you wrap your C++ code then to Python to make it accessible from the easy to use Python interface. What do you have to do in the CMake? It's actually very easy now. You have to do find package and resolve, and you do this config required, which basically says you need to have ngSolve installed, else it will throw an error. And here you can give some paths with like default installation locations that it will automatically search for, and if it wouldn't find them there, the user will get an error that they have to specify the ngSolve directory where it is installed. And then you use this add ngSolve Python module function that we added in the ngSolve package. So basically you get that from the ngSolve package, and it basically tells the compiler how to build, from linking, from include flags, from everything, your C++ files, which you then specify, and here's just the name of your module. And you can use this snippet to make it automatically be installed into the ngSolve directory. So basically, if the user doesn't give an installation location, it will be installed with the ngSolve package. So that's basically what you have to do configuration-wise, and then yeah. No, it does also work with installers. I know that there is an issue with the Linux Python package that I think it has problems compiling on some other distributions. So the Python package itself works, but it might be that on Linux you need to compile from source or use for example, on Ubuntu, the Ubuntu installer.
Yeah, I mean, pip is a problem.
Yeah, exactly. So the ngSolve pip package does not work on all platforms to compile extension modules, but the rest works, I think, as far as I know. Mac, Joachim?
Everything works on Mac.
Okay. So let's go then to Python bindings. For the Python bindings, we usually have the flavor, but you can do it anywhere, that we create a separate Python underscore export or Python underscore module name C++ file, where there is one block where all the Python export happens. And it is started with this, so you include the PyBind 11 headers, or actually you just include the ngSolve PyBind, the ngSolve Python headers. And then you have this block with this macro PyBind 11 plugin, give it your module name, and basically these 2 lines of code. And in between you export all your functions. Just very shortly how to export stuff to Python. You basically say function name and then a lambda function with the C++ stuff, or for a class, you give the class, the C++ class, then you give the holder type. So in C++ for memory management, we use shared pointers with most of the objects that are wrapped to Python. So that basically guarantees that you can keep the objects in C++ and you can keep the objects in Python floating around arbitrarily, and only if all the objects are dead, actually the C++ destructor will be called. And you can specify base classes. So it will then also automatically know that in Python it is derived from coefficient function, for example. And then you give it a name, a documentation string, preferably not only docker string, but something meaningful. and a constructor. So there is some default constructors available. You can also construct them with lambda functions. For more on that, look at the Pipeline 11 documentation. It's quite explanatory and well documented, so I won't go into more detail of that.
Do you have to wrap all the methods?
Yes.
Not always the one you want.
The one you want. And we did that. So there's like two different options of wrapping to Python. There's kind of this Swig stuff where you basically wrap everything from C++ and it kind of copies the structure of your C++ code. And there's this Python stuff where you separately have to wrap everything. We chose that way because then we can define a nicer interface than you have in C++. I personally, I don't like so much the Swig stuff because then you will get really ugly Python interfaces.
So what was the first option? What was the, besides Pipeline, what was the first option?
Swig is also very popular in that. So Swig basically just looks through your C++ code and exports everything to Python with the same names and yeah, and we actually, there was a lot of work put into like making Python neat and Python-like and not C++-like. And if you don't want to do all that, there's actually an even easier way, but it also has its, so nothing comes for free. There is one function that we export in this ngsolve fem library, which is called compile Python module, and you just can give it a C++ file that would compile in such a project, and it does basically everything for you. It's really, so I really recommend it for people that just want to distribute the code to someone as a showcase, for example, because you don't have to send them a package, they don't have to compile anything, they can just like get a Jupyter notebook and execute it. But of course, if you want to develop yourself, you don't have autocomplete, you don't have all the flexibility that you have if you compile your own project. So I think it's more for like showcasing small examples. But of course, for like best perfect example is a classroom example that you want to distribute with your students. It's way easier, they don't have to set anything up, everything will be done for them. So far, any questions? Building and Python exports? Then only shortly on this my little project, my little ngsolve project, which is basically a tutorial which gets you into C++ programming in ngsolve. So you see how you can define your own elements, your own finite element spaces, how you wrap everything to Python. Yeah, so the like differential operators, stuff like that you see in there. We will have a detailed look tomorrow into this. And it's also in the documentation, the online documentation, so if you want to look it up. And then shortly, let me explain the code structure of ngsolve. It also has developed a little bit. Basically, NetGen and ngsolve both use the ngCore now as a library. That has been some recent improvement because before both of them had a separate implementation of arrays and tables and stuff like that, and you had to transform between them. Now they have a common implementation in this ngCore module that actually is included in the NetGen source code. And there's also the task manager and stuff like that, and it's also available as a separate library. So if someone wants to just use some of the functionality from ngsolve, like the task manager and like arrays, they can just also use this ngCore module as a standalone library. Then in NetGen is structured into the different geometry models. As we have seen, like our focus was now on Open Cascade, but you also have like the STL geometry and CSG, and also I forgot here the old 2D geometry and the meshing module. In the meshing module, everything related to meshing is implemented. The ngsolve module, I've reduced it a bit because the old ng standard and ngsolve modules are actually not really relevant anymore, as far as I know. I don't see many relevant parts there. So it's basically structured into two parts. One is the fem and one is the com. And you can think of it as fem is everything that is local, like element local. For example, integrators, finite elements, integration rules, stuff like that is there. Comp is everything that puts together the local stuff. So like bilinear forms, finite element spaces, grid functions, stuff like that is in the comp, computational. And Linux. Linux and basic Linux. I thought something was missing. And there's also Linux and basic Linux. Linux is all the linear algebra stuff, and basic linear is the basic linear algebra stuff on the small level. So basic linear algebra stuff is like dense matrix multiplications, everything small. Linear algebra is all sparse matrix, large solvers, systems, stuff like that.
Can say something where the mesh class is. There's the two meshes. The NetScan mesh.
Yeah. In comp there is also the mesh access class, where we had the discussion yesterday a bit, that in NetGen, basically the NetGen mesh class only has information that is necessary for meshing. But when you do finite elements, to efficiently do finite elements, you need a bit more. Like you often need connectivity information. You need, for example, also the boundary information more accessible. More, you need some data structures that are not necessary in meshing, and we build them only in this ngsolve mesh access class, which is in Python then wrapped as ngsolve.mesh. And it will be constructed in the constructor of the mesh access class in the comp module. You want to add something there? Yeah, and then like, okay, now you have your Python code, you want to look into the C++ implementation behind that. How do you find that? So I'm trying to do that now in Visual Code. Don't blame me for being a bit slow in there. That's new. So what you do is basically you go, let's go into some tutorial and look at the Poisson equation here. So we want to see the bilinear form. So what you can do is I can ask Python for the type of the bilinear form. And if everything is working now, I can execute it and see. Yeah, I need to print it, thank you. And I will see that it comes from a certain module. So every one of these C++ classes comes from a module, and I see it comes from ngsolve.com module. So what I will do first is I go into this comp subdirectory, and in every one of these subdirectories we have some Python underscore files, and you usually want to look at the CPP files. So I have two here. I need to search in one of the two. The first one is called mesh, so I assume it's not that, but you can look in both. But except from comp, it's actually only one Python CPP file. And then in there, you search for a string bilinear form. So I usually always search for also the ticks and the word. And then you will find the wrapper to the bilinear form. And from there you can also search, for example, of the implementation of the I don't know, assemble function. And then you see the C++ code behind, that is called behind. And from here, if I set up my project correctly, I can jump to the definition and look through the code and see what actually happens behind the scenes in ngsolve.
Go to the Python, back to the Python binding of the assemble short command on the local heap. So we don't see it in Python, but it's all in C++. Is there a difference between the Python interface and C++ interface?
Yeah, wait. That was in, I don't. Here, assemble. Okay. In assemble allocation, it's the same. Here you get this global local heap argument that actually is only on the C++ side, and it's basically a stack, a larger stack of memory that is used for efficient memory allocation. So we hide all that ugly C++ stuff from you in Python, and we use some globally available stack for allocation of these runtime quickly.
You don't have to worry about the Python.
Yeah.
You don't see it.
So I think I did that. So since we have how much time? I'll go quickly over how to find your bottlenecks. So if you want to find out where your code is, or what is actually the bottleneck of your code is, there's one thing to do, and it's quite easy. Okay, I will go to Emacs because I'm quicker. What you have to do is, you have here this task manager. Put it up a bit. You specify another argument to it. You give it some integer. This is actually a size for the memory that we will allocate to store traces. Then you execute your file, and that will give you 2 additional files. So it's done now. So when I open this folder, I will get this ng0.html and the ng0.trace here. And these 2 files contain some information about the runtime performance and so on of my code. So let's start with the HTML. And what you get here is kind of an overview where time is spent in your code. So when we look at it, all the time was like 5 seconds in this task manager run. From that, for example, were like 3.4 seconds the CG solve. And when you hover over it, you will see it's a little bit bad readable, but you'll see apply BDDC preconditioner was here 2 seconds. Most of the stuff, it has been called 54 times with an average runtime of 38 milliseconds. And that's kind of, so you can shift your focus to the routines that actually cover most of the time of your code. Here it's actually, when I ran it before, maybe it's because of screen sharing and everything, that now the CG solver covers more, but it was actually almost half of it before. But this is one important thing to note. It doesn't mean that matrix assembling is actually taking so much, because you also have to look what is in matrix assembling. And as we know, one of the reasons that we had to build the preconditioner before assembling is because in the assembling a lot of preconditioner stuff is done. So you see here in the matrix assembling, actually only 1 second of the 1.5 is actual matrix assembling, and some part, the rest is BDDC stuff already. So we are building some parts of the we're building the preconditioner during the matrix assembling. So you'll see that also here. And then the second file that we have is a trace file. So it's called ng0.trace here. And you can open it with this tool. It's called Vite. Virtual something trace explorer. And here you see like a linear runtime evaluation. So if you double click here on this function, on this bar down there, you will get a window that says values matrix assembling, timing from this milliseconds to this milliseconds. It was 1.5 seconds. And if you go down here, it will get finer and finer grains. So you will see that this part, what color is this? Greenish part is the volume, so matrix assembling volume. So you will see that you have here, so this is only the iteration over the volume elements. And what you see up there, so from here to here, is what your different threads are doing. So you see that this is quite well optimized because all the threads are actually doing something all the time. If you would have here one large bar and then some short bars, it would mean that you just didn't color your elements well, or you did something that actually had that all the other threads has to wait way too long for the one thread to finish and work it up. So Joachim spends a lot of his time optimizing these things so that they look like a nice colorful wall of.
There's a gray region here.
Yeah. So the gray region is the one that is not parallel. So you see that this matrix, the matrix assembling finalize. So here, and what we actually see if we go down here, this green bar is the minimum degree ordering of the direct inverse inside the BDDC on the lower order degrees of freedom. So that's one part that cannot be parallelized. So you also see that here in the trace files. Yeah. Yeah, and only shortly, like how can you add these things? Basically what you do is you add a static timer with a name, and then in the block that you want to time, you add this region timer reg with the timer as an argument, and then these blocks will end up in your graphs. You can also do that in Python, and there's even a decorator for functions. It's called add time function, and then you also have your Python functions in this hierarchy. Yeah. So that's it from me.
We're going to depth tomorrow.
Yeah. Well, if you have any questions, you can come.
Yeah. Just got this. Yeah, cool.
Okay. I think I have to do the. Okay, I think you have been on this webpage for a while. On the documentation, you find two links to major documentations. One are the tutorials we have been using over the first few tutorials. At the end of the appendix, you find also some recent technical stuff like parallel computing with Task Manager. There you find also how you can install this Vite, for example, documentation on WebGUI with the key output. I will switch between this documentation and the other one. Oops, sorry. And there are the interactive FEM course, the IFEM material, which is a page into a GitHub where a lot of lecture material, where we were teaching finite elements, how the method works, and during teaching how to run it in NGSolve. This is one more for the learning the finite element material, also theory. The other one is more for the experts in finite element, how to use it in NGSolve. I'm switching now between these two courses. Okay, so the phone. Okay. Okay, I want to start with the IFEM. What is the finite element course, where you learn mixed finite elements and so on. And there is a section on parallel solvers also. I want to spend now half of my time with MPI parallel solvers, how you run ngsolve MPI parallel. You can set up a Python file and submit it as a cluster, or you can run also MPI parallel in a Jupyter notebook using MPI for Pi and IPy parallel. So I can start now an MPI cluster on my laptop here with 4 nodes. This is a first tutorial on MPI parallelization without ngsolve, just showing how you can start a cluster using IPy parallel. It gives you a C, what is a representation of the cluster. I can now define Python variables in each of the processes, of the 4 processes. I can do some computation with every running process. This %px command sends a cell to the processes of the cluster, so every process is just doing the multiplication. At the end we can query the result back to the Jupyter front end. You can use MPI for this. You can load MPI for Pi. You have the world communicator. These are features from MPI for Pi, taking process 1, 2, 3 out of the team. You can do point-to-point communication, for example. You can do broadcasts. This comes from MPI for Pi. Okay. How do we use it? Okay, no, sorry. Yeah, second part. Okay, starting again the cluster. For jobs should start on, yeah. Importing MPI for Pi. And now we want to generate the mesh. We can generate the mesh on the master process and distribute the mesh in the cluster. Okay, we are checking with the MPI for Pi rank. Are we on rank 0? Then we generate the mesh of the unit square. Then rank 0 has the unit square, and we can distribute it within the cluster. All other ranks do a receive and get the part of the mesh from rank 0. And then we can do mesh refinement in parallel. And the netgen mesh, and now we have the ngsolve mesh. I do a print, so I get output from all of the 4 ranks. And process 1, 2, 3 got this number of elements. The rank 0 is just the manager, it sends all work to the others, it only does management job. Okay, then we can use MPI for Pi, for example, to reduce the local number of elements, and the reduction sums up the local number of elements to the global, and globally we have this number of elements. We can also retrieve the mesh, which is distributed on the cluster, back to the main process. So this is internally done by pickling, so the mesh is pickled and the front end is receiving the full mesh, and also the individual pieces of the mesh. So we see how the mesh was distributed and then refined uniformly in parallel. If we have the mesh distributed, we can define, as usual, a finite element space on the distributed mesh. So we get the H1 space on all of the subdomains. The meshes know how the vertices are identified. The finite element space inherits this information from the mesh. The degrees of freedom are shared at vertices, on edges, faces. We can sum over the local degrees of freedom, which are of course more than the global ones since they are doubled. We can do some simple operation where we can interpolate a function x times y on the square. We integrate. We get output from every process, so everyone is integrating on its own subset of the mesh, and the integrate accumulates across the, so all get the same result. We can also download the grid function from the cluster to the front end, so we can look at the solution, or in this case just the interpolated function, on the globally and on the individual pieces of the distribution. For example, rank 1 got this subdomain, so we see the function only on this subdomain. what we can do is we can define a discontinuous finite element function, so a piecewise constant or a 0 L2 function, and we set the local vector to the rank of the processor. And if we look now at the visualization of this L2 function, we see the partitioning. So rank 1, rank 2 is green, rank 3 is red. How do we get this identification of degrees of freedoms? We have an object parallel dwarfs. This parallel dwarfs knows degree of freedom on this vertex on my rank is the same as the degree of freedom 17 on Christopher's rank. So we can retrieve this parallel dwarfs information from the finite element space. We can expect it from Python. So rank 2 is saying, oops, with process 0 I'm sharing nothing, with process 1 I'm sharing this degree of freedom, with process 3 I'm sharing this degree of freedom. All this identification of degrees of freedom are stored in this parallel dwarfs object. How do we store vectors? If you have a solution vector, if two processes share the same vertex, they should have the same value at this vertex. If you compute right-hand side vectors, we compute the element-wise contribution of the right-hand side. So we do a sub-assembling. So we assemble the vectors on the subdomains, and the sum of the values at the vertices gives you the correct value for the right-hand side vector. For this, we have consistent and distributed vector types. It's like element assembling with its connectivity matrices. So a right-hand side vector, a right-hand side vector is the sum over local right-hand side vectors. Like on the element level, the global matrix is the sum over element matrices with the connectivity matrices, where the connectivity is now from the subdomain to a global enumeration if you want to have one, but usually we don't have one. Okay, if we assemble the right-hand side vector, we print the vector. The vector is a distributed vector. We see the vector is a distributed, and every process prints its own part of the right-hand side vector. If we have a grid function, a consistent vector, logically the local contribution is the connectivity matrix transpose of this of the global vector, and it's very useful if we do inner products. If we do inner product between a distributed vector and a consistent vector, you plug it in, you see that you can do local inner products, just standard sequential inner products, and sum up the local inner products to get the global inner product. It's done here. This is the built-in inner product of the parallel vectors, get 1. If it's a parallel inner vector, we can retrieve the local vector just living on the subdomain. We do local inner products, and if we sum up the local parts of the inner products, we should get the same sum. So locally, we compute these inner products, which are depend on the distribution, but the reduction, the sum of them gives us the same. Matrix vector multiplication is very convenient if U is a consistent vector, and the result should be a distributed vector. Then in this case, we can just compute the local matrix vector product without any communication. Kind of vector operations. If we add vectors, if both of the same type, consistent or distributed, we can just do a local addition. And we can convert also the types. If it's a distributed vector and we want to make it consistent, we have to do the reduction at the coupling interfaces, so it needs communication. If we have a consistent to a distributed, we can just divide by the number of processes at this vertex. So if we start with a vector distributed and cumulate it, we end up with the same vector again at the end. This is going on behind. How much do we have to know about this? Okay, we want to make a simple iterative method, a Richardson method. So instead of doing an explicit master generates, distributes the mesh to all the workers, we can also do call generate mesh on the communicator. then that's internally message generated on rank 0 and distributed to all the workers within the communicator. Same as before, assemble a system. It looks the same as we do it in sequential. The only difference is that we provide the communicator here to the message generator. We want to do a simple Richardson iteration, residual, preconditioned residual, and update. Okay, so we are creating new vectors by asking existing vectors to create a new vector. We have the vector from the right-hand side, from the linear form, which is a distributed vector. If we ask it to create a new vector, we will get a distributed vector. We ask the grid function vector to generate a new vector. Grid function is a consistent vector type. It generates a consistent vector W. And here's a very simple Richardson iteration, computes the residual, applies a precondition to the residual, compute inner products, and yeah, this is a convergence. Where does communication happen? It happens in the application of the diagonal preconditioner, where the diagonal summed up, and it has to convert from the distributed to the consistent vector. Okay, we can. Looks familiar solution. Or you just call the conjugate gradient solver. Now with this parallel matrix, the distributed preconditioner, apply to the parallel vector. You call the CG solver as you do it in sequential case, and it does also vector type conversion accumulation within the components for you. And this final solution. Okay. You will see much more about Betsy in a few minutes. We have a
how many processors is this efficiently scaling up to?
10,000. 10,000. Okay. And we didn't try more, so 10,000 was scaling. Right. Of course, not from Jupyter. Not from the Jupyter notebook, of course. But we make a Python file and distribute it to the cluster. So this Jupyter notebook and parallel computing is mainly for teaching and tutorials and testing. So we can run this on one node of the cluster. Okay, we can convert our matrices to Betsy matrices. Let me quickly show this, starting again. The same, refining in parallel. We are importing the Betsy to Pi for Pi interface, building our own system. And now we're using all these Betsy for Pi instructions to convert our local matrix to a Python matrix, go via CSR to create the Betsy matrix via CSR format. The parallel DOFs information is translated to an index set object in Betsy. We can create now a distributed Betsy matrix by these instructions here. We can send vectors back and forth and run Betsy Krylov space methods. And we are now running via the Betsy for Pi interface the solver in via Betsy. You have to know a lot of if you always want to do it again and again. So we have a compact Betsy interface. We started with hiding everything into or putting everything into an interface layer. Betsy to Pi. So we have Resolve NGS to Betsy interface, where we can just say create Betsy matrix from the ngSolve matrix with identifications and the vector identifications, and this creates a Betsy preconditioner to be used in ngSolve. I'm going over this quickly since Umberto will say much more about the further development of this ngSolve to Betsy interface. And the last one is an example how to use it to solve Stokes equation in parallel. So I have this flow channel, open cascade 3D geometry. solved via Petsy. We are setting up a Stokes problem. We have an vector H1. We have a block diagonal matrix for the A block. 3 copies of the same matrix. So BFA1 is just a scalar Laplace operator. Okay, and we have the 3. Okay, the A matrix for Stokes consists of 3 copies of the same scalar Laplacian, which we want to embed in a larger matrix. For this, we have restriction and embedding operators, restricting the product space to its component space, or extending a vector from the component to the product space, which also take care of the identification of nodes among the processes. Creating block vectors and running a saddle point solver, in this case the Premel-Bashak CG, and you see we have solved the very simple method Stokes in 3D. This was this flow channel. It was useful, so also we have been assembling the hard work of the solver, of the preconditioner is sent to Petsy, so we could use a good AMG via Petsy. Okay, so far about the MPI stuff, which I want to show from here. Some more I want to show from the teaching material is some explicit time stepping methods. For example, with mass lumping and explicit time stepping, you can do quite fast time stepping. That's simple. Okay. Here we do mass lumping. So the mass matrix is diagonal. We had this topic also specifying integration. So the lumping finite element space knows the lumping integration rules. So we can give the dx, the integrator, the integration rules coming from the mass lumping, higher order mass lumping. Stiffness matrix as usual. We create the diagonal smoother, so the mass matrix is diagonal, so we can invert it by just taking the Jacobi preconditioner and run here a Verlet time stepping scheme. I can run it, and I think it's not. So this is how. Oh. Okay, so looking. So with this higher order explicit time stepping, the dispersion is quite good and performance is also not that bad. And we can, for example, do the performance analysis using Witte tracer. So this method is very simple, just applies on matrix applications. So this is very, let's stop it here. Very convenient also to send to accelerators. And the second part of this talk is on using CUDA devices. Now I'm switching to the other part of the documentation, to the iTutorials, where in section 5, we have now a relatively new session on CUDA computation. So I'm jumping into the second part already with explicit time stepping. We are using a DG method for the wave equation. Pressure time derivative with divergence and U time derivative with gradient of the pressure leads to this symplectic structure, mass matrix for P, and U is the discretized gradient operator and the transpose of the gradient operator. The differential operators come from a DG binomial form with element-wise gradient P times V on every element, and the jump terms, which are written in terms of boundary integrals of the mean value minus the local value. The typical DG bilinear form. The neat thing is that we can build the matrices such that they are universal, but means that every element matrix in the whole mesh is the same. So we don't have to store the big sparse matrix, we're just storing the matrix for the reference element and can use the same matrix for all elements in the mesh. Okay. Setting up this 3D geometry, so it's a box with a sphere cut out, so it's a box and a sphere cut out. We're using this higher order TG, so we have the discontinuous L2 space for the pressure, we have a vector L2 space for the velocity, and the trick is that we are not doing a one-to-one mapping, but we are doing a Paola mapping from the reference element to the physical, which makes this integral universal. We treat the mean value as a new independent variable, so we are building also a Balnaform, a matrix between the facet variable and the normal trace. So we need a facet FA space. Christopher has shown the trace operator also already yesterday, so from the L2 space we can generate a trace matrix which gives us the linear operator from the L2. If you have an L2 function, a coefficient vector of an L2 function as input, and you want to represent the jump on the facets by the polynomial space on the facet, which is given here, not the jump, the mean value, we get this linear operator. You can think of it as a matrix. At this point, we don't tell you how we store this matrix, how we represent this matrix. It's also a matrix which is independent of the geometry, so we're just storing element matrices for this. Now there comes the actual Balnaform. We are building the Balnaform for the element term, so one is between the element space and the velocity, and we say geom-free, so we only store reference element matrices. The same for the term involving the mean value. And the complete gradient operator is now the element term as a linear operator plus the composition of the trace Balnaform with the trace operator. This means composition of linear operators and adding them together. The finite element space provides the mass matrix and inverse mass matrix with some neat implementation of this. So knowing the basis functions are orthogonal on reference elements using tubular basis on tetrahedral elements, we have orthogonal basis functions. The matrix is diagonal on affine elements, and you can do some other tricks on curved elements with some factorization, which is all in here. And then you can do a time stepping, what is a leapfrog in this case. So operator 1 is solving the mass matrix for the velocity with the gradient operator and solving the mass matrix with the divergence. Divergence is the transpose of the gradient, transpose linear operator. Okay, something was not executed. Again. This is now explicit TG time stepping for a three-dimensional wave equation. So it's running as a volume. You see the scattering of this spherical void here. Okay, already quite fine on the MacBook. Okay, now I want to do this time stepping on a CUDA device. For this, we import and solve NGS CUDA, that is an extra library. Okay, and I don't have a CUDA card in the MacBook here, so sorry. What do we have to do? So we have this linear operator, mass inverse composed with the gradient, and this composition of linear operators is now sent to the device. When you say create device matrix, it sends this linear operator to the device. It copies a sparse matrix over if it's sparse matrix, if it's some diagonal matrix, and the diagonal matrix there. If it's a sum of matrices, it sends a sum of matrices over there. We create device vectors for pressure and velocity and just run the same code on the Python level, and all the operations are done on the device without copying data back and forth, except we want to copy it back for visualization. Okay, now the same code runs on my fake device. Since I don't have a device in here, it's just running on the CPU again. What is actually the operator? This is mass matrix inverse gradient, And the internal structure of this looks like this. So the whole thing is a product matrix, that means a composed operator, this size, a scale, this was the time step, the sum of two matrices. Okay, the mass matrix is a block diagonal matrix, a 3 by 3 block diagonal matrix due to this Euler transformation. It's a block diagonal matrix with block size 3 by 3, stored as structure of array format, which is better for the GPU. We have constant element by element matrix, which are the same element matrices for all elements. So this constant matrix, which is applied to all elements in the mesh with the indexing them right. So we can use matrix multiplication for the application of the divergence matrix. So we have now a handful of different types of linear operators. These must be implemented for the device, and then we can send this complex operator to the device. And I did some time here, so now locally it takes now 50 milliseconds. If I'm running the same notebook on a A100 device, it takes 2 milliseconds, so quite some improvement. If you do time domain PML, okay, this is a waveguide here. So I'm sending in a wave package here. It's following the channel. And you see this is a split ring resonator, part of the wave package coupling to the inner ring. We have a PML there, time domain PML there, which means the wave is absorbed in this layer. PML means there are some additional variables coupled via ordinary differential equations out there. Don't have to know the details, but they are all written in the solved language and discretized in terms of these linear operators. You see this wave package was absorbed here. The trick is the whole thing, also with the PML, is represented in terms of linear operators, which can be sent to device. So people who know about PML, and people who know about CUDA optimization don't have to know the other field, and they can just combine their knowledge. And the last example, if we solve nonlinear conservation laws like Euler equations, it's hyperbolic conservation laws. So we have the flux of the Euler equation, and we do it on CUDA. Mesh generation. Here is the flux, the flux of the Euler equation with density, velocity, energy. Okay, we set up a binomial form for several terms of the Euler equation. So locally we have the flux in the product with the gradient. Then we have the numerical flux with normal components and so on. We can compile everything to some matrix-free tricks. Okay, here we have the complicated formula for the conservation law. We compile this, and if you also this okay, you see the density package spreading out, finally forming shocks. The operator is quite complex also, but it has now also the application of a nonlinear operator. And if you search for some nonlinear term, where do we find this? Yeah. So in the integration point, we have to apply the nonlinearity. This is also fit in our framework of linear operators, also it's nonlinear. How do we treat this on the device? So we have the flux as a nonlinear function. We linearize this expression. We get the program of step 0 compute this, step 4 compute this. In the step 22, we do this scalar times vector multiplication. We have one step after the other. For this, we usually generate the C code, send this to the compiler to generate code for the CPU. But now we can send this code to the GPU. Running over it. we are producing C code like this for the individual steps, and just at the header, which is now made different, so it's now made a CUDA kernel function, then it requires a CUDA compiler, and can now apply also the nonlinear flux on the GPU. And with this, I'm done with this parallelization CUDA device computations. If you want to see more about this tomorrow, I will do a mini tutorial, and we can do via this MPI and also CUDA stuff together. You find these tutorials already on the homepage. You can use them on the CurbSim Jupyter Hub or on the VSC Jupyter Hub. On the VSC you have the CUDA devices also, and you can try it out yourself. It's quite recent stuff, and more is coming soon. And now we continue with enriched, larger PETSI interface. What Umberto and colleagues from the PETSI team have developed over quite recently.
Yes. Well, there's been a lot of development since I arrived. I forgot about that. Can you send me a link?
It's also fine if you don't.
Okay. I will share the slides. Oh no, I cannot. Screen recording. Take screen. Yes. Video. Screen. I'm recording. I just need to set the preferences in such a way that I mirror. What is the display? Display, mirror, apply. Okay, so the new ngSolve PETSI interface, we developed it with Stefano, Patrick Farrell, and me. I'm a PhD student at University of Oxford with Patrick. So let me tell you a bit about the ngSolve PETSI interface. So there is something that came before this, which is the fact that at Chaos we were interested in using ngSolve to solve eigenvalue problem, and a good interface for solving eigenvalue problem is LabC, so we had to start getting some experience with the NGS PETSI interface. And at that point there were already two ngSolve PETSI interface. One was the NGS PETSI, which was a C++ interface, and the other one was the ngSolve 2 PETSI, which is part of ngSolve, and Joachim has already showed. So there are already two interfaces. I will try to convince you by the end that this should be the one that for you to use and the final one to work with. But yeah, so we started working on a NetGen 2D-Mplex interface to do adaptive mesh refinement in Firedrake, because it was not possible before. So this was the reason why we got interested in it. We got PETSI DMPlex transformation wrapped into PETSI for Pi, which was not there, and somebody, I don't remember who, told me it was interested in doing alpha splitting and some sort of refinements. We can do it through this. I will show you how. We got the DMPlex to NetGen interface for ngSolve, so now you can use any DMPlex, so also any object that comes from an HDF5 format can be loaded into PETSI and then as a DMPlex and then brought to ngSolve, which is HDF5 is the standard for DOE, so that could be interesting. And so we finally got our ngSolve DMPlex merged into Firedrake, and then we went to Phoenix, and the Phoenix people were interested in using NetGen as a mesher, so we got the ngSolve DMPlex also for Phoenix. And at this point we wondered, can we actually put together more feature from PETSI into ngSolve, and not only the DMPlex? And I will try to answer this question now. Okay, so what are the reason why we're interested in PETSI? We're interested in PETSI for scalability. It's extremely efficient in parallel. It has got a ton of Krylov solver. I will show you some of them in a moment. It has got a ton of preconditioner, and I think this is one of the reasons why Joachim was originally interested in this. And it wraps in a very efficient manner, an easy manner, Hyper, MUMPS, H2 Opus, Intel MKL, you choose. So if I've got to install MUMPS with ngSolve, or I've got to install Intel MKL with ngSolve, it might be a pain, or might not. If you have a pip install that does that, great. If you don't, it might be a problem. PETSI could be a pain, but in one run, essentially, you have an interface to all this library, and I will show you some of them. And yeah, so this was the reason why we were interested in using Petsy. Disclaimer, this is not gonna work with the pip install. So you need to build your ngSolve from scratch because we need MPI support. And since we need MPI support, you need to, when you build from scratch, turn on the use MPI flag. So this is important. If you're interested, you can find a Docker image. This is already done, tested on the Docker image. Or tomorrow for the tutorials, come to the tutorials, I will be using Jupyter notebooks, either from SerbSim or from the VSC. So everything is already set up there. Thank you, Matthias. And Petsy Slapsy. Of course, you need to have compiled Petsy and Slapsy with Slapsy for Pi and Petsy for Pi respectively installed because all our wrapping passes through Python. I'm here if you need to install this, so ask me, but you will find all the tutorials on how to install this also in the read the docs for NGS for Petsy. And I shared all of these, the slides, the codes, and the link to the documentation in the ngSolve group chat, so you should find it there. Okay, so what are the basic components of the ngSolve Petsy? Well, what are actually the basic components of Petsy that we are interested in wrapping? So we're interested in something, right, or that we have already wrapped actually. So it's the PetsyVex, PetsyMat. You have already seen this in Joachim tutorial. We have the Petsy KSP wrapped now. We have the Petsy Dmplex, and we have the Slapsy APS, respectively. Vector matrices, Krylov solvers, meshes, eigenvalue problem. So those are the three components we're interested in using through the NGS to Petsy interface. Now PetsyVec, very easy. It's a bit different from the construction that Joachim showed you before because now you only need to pass as a fess. Once you pass as a finite element spaces, it knows all the information that it needs, and so it's able of mapping a Petsy vector from an ngSolve vector just for this information. Sometimes you might not have this information available, like in the case of the preconditioners, so you can, if you look at the code, you can actually not pass this, and you just pass it to the parallel DOFs and the free DOFs, and it knows what to create. We have a PetsyMat object. PetsyMat object is essentially, you start with a bilinear form, you get the matrix, the NGS matrix out of the bilinear form, you import the matrix constructor from NGS Petsy, you pass it to the matrix constructor, and now you have a matrix. Now you can easily host this on any GPU thanks to the Cocos support in Petsy, which will allow you to use NVIDIA, Intel, AMD GPU, whatever you like. There is also native CUDA support from what I remember, but Richard can correct.
There's also native HIP support.
Ah, there is also native HIP. Okay, I checked the roadmap too long ago. So there is also native HIP support. So this is interesting, right? You have seen how to solve the Poisson equation on a device, on a CUDA device, and all the implementation is done in CUDA. Now, let's say you don't have a CUDA GPU and you still want to use a GPU. How do you do it? Pass through Petsy. KSP solver, very easy, linear form, import the Krylov solver. This is actually what is the interesting feature of the new wrapping, which was not in the past wrappings, which is the fact that you can pass the solver parameters. So essentially, Petsy has been built in such a way that through the command line, you can configure most of the solver that are in there. And if you pass those arguments to the solver parameters, you can reconfigure the KSP before actually running the solve. Yeah.
Back one page.
Yes.
Which matrices are supported today?
Today we have IJ, Q-sparse, dense, and
what kind of ngSolve matrices can you write by this? So
the parallel, sparse matrices. Parallel sparse matrices.
What is element to element constant matrices? Maybe not today, but
not today, but soon.
Tomorrow.
Easily tomorrow, very easily tomorrow, but we need to sit down and have a look at it.
A composed linear operator?
No, that's a bit trickier. I wouldn't know where to start. Probably I would start creating a matrix out of a Python context and wrapping in the Python context your idea, but it's not going to be done in one day. I need a bit to think about it.
We can talk about it tomorrow.
Okay, we can talk about this tomorrow. Actually,
the idea is to have all these composed operators, send them over to Petsy, and let you do that.
We could try. We could definitely try to have a chat about how to do that. Now, one feature of the PetsyMat that was not there before, and actually this is Stefano's work, we can actually work with non-square matrices. Before, the NGS2 Petsy only supports square matrices. Now you can also handle non-square matrices, and this will become useful for one of the features that I will discuss later on. KSP solver is the solver I was telling you about. So for example, here I'm solving with mumps, and I don't have mumps installed in my ngsolve installation. I ask Patsy to take care of solving stuff, doing a mumps factorization. Now, you're gonna ask me, yes, everything is nice, but why do I want to use a Patsy KSP? Well, you want to use a Patsy KSP because you have 1, 2, 3, 4, 5 pages of solvers that you can actually access pretty easily. Of course, each one of those has got its own flag. You need to go into the Patsy manual, check it out, understand how it works. But this gives you access to a wide variety of Krylov solvers that you might not have immediately, or you will have to code on yourself. And when you know it better than me. When you are implementing something, there is a lot of dirty tricks that you might be playing that you need to know, and you know if you're in the field. So here, instead, all those stuff has been implemented by someone else, and you can access it. Same idea. Now it's for preconditioner. So we want to use any Patsy preconditioner inside of ngsolve. How do we do it? Well, we construct. This is literally an ngsolve preconditioner, the usual construction. The matrix you want to precondition, the flag of the preconditioner. Now the flag of the preconditioner is Patsy PC. As soon as you pass a preconditioner with the Patsy PC flag, it assembles the preconditioner in Patsy, and then you pass the PC type or any other flag that you might be interested in passing through to Patsy as a command line argument. You pass it as an argument as a kwargs dictionary. So the kwargs dictionary that you get here becomes your solver parameter. And so, for example, here I'm using Hypre. I'm asking Hypre to assemble my geometric algebraic multigrid preconditioner. Well, it's not geometric in this case, it's algebraic preconditioner on a matrix A. And so this runs outside in Hypre. And then I get my grid function, and yes, and I run CG. So I'm running, this is the CG method from ngsolve, because I'm interested in using an ngsolve method with a Patsy preconditioner. Matrix, right hand side preconditioner, and the preconditioner now it runs on there is geometric algebraic multigrid from Hypre. Now, why am I interested in this? Because Patsy wraps a lot of preconditioner, and they have been implemented already. You have the standard Jacobi, point blow Jacobi, very standard things. You have some interesting preconditioner which might not. You can of course do any LU, incomplete LU through different type of factorization. So for example, if you're interested in ILU, you can compute it through super LU, sequential LU. You can compute it through mumps, which is not there. But so you can do this type of things. You can actually, which is something that I was very interested in when I was at Chaos, use hierarchical matrix. So H2 opus matrices if you have a dense matrix. Let's say that at a certain point you have a dense matrix and you want to precondition this dense matrix, you do a hierarchical representation, and then you construct your preconditioner on the hierarchical representation. So that's a feature that you have in there. And you have SPI. Actually, the real reason why we started the Patsy PC business was because Joachim was interested in using SPI, and SPI is coded in many different places. One of them is Patsy, and so you can use it and wrap it. I recently heard a talk about SPI, and I asked, and SPI in mixed arithmetics. Patsy not capable of doing mixed arithmetic, but it was very interesting. So I got really interested in using a SPI precondition. And yeah. Now we come to the dmplex object, so the meshes. How do we go from Patsy mesh to a dmplex? So DM is distributed mesh complex, dmplex. So we create a mesh mapping. Here what I'm doing, I'm interested in using a dmplex transformation. So there is a set of transformation like Powell Sabin, Alfred splitting, regular refinement that are available in Patsy. Also you can do metric refinement, but that's another story. We create a Patsy transformation. We set the type. In this case, I'm doing a refine Alfred splitting, 2 or 3D, doesn't matter. We set the DM, which is we go from my map and I grab the Patsy dmplex, give it there, apply the transformation. I get back a new Patsy dmplex, and I convert my Patsy dmplex into a next-gen mesh, and then I grab it in ngsolve. And I can do this. I can do Stokes with a P2, P1 discontinuous. P2 continuous, P1 discontinuous, we all know it's not stable. Actually, Joachim showed us yesterday that if we try to do P2, P1 discontinuous, the UMF pack fails because we don't have the inf soup. We do an alpha splitting, which is something that Jay likes, and we get back I like it too. And we get back Scott-Vogelius elements which work because they are in a complex with HCT elements. Okay, I will show you how to do this tomorrow in the tutorial with all the codes, but it's pretty easy. And now I come to the last thing, which is the APS. The APS interface might seem a bit convoluted, but the reason why it's convoluted is it's built in this way because we want to wrap in a single eigensolver both the PETs, that should be SLAPC, sorry, the SLAPC APS and the SLAPC PEP, which is normal generalizing eigenvalue problem and polynomial eigenvalue problem. We are trying to map everything together, so you pass the pencil, sorry, so the mass matrix A, so mass times lambda. If you put another object in front of here, it would be lambda squared. So we pass the pencil and flags for SLAPC. Here, for example, we are targeting the smallest magnitude near to 2, and we are using a spectral transformation, so we are actually solving A minus sigma, where sigma is the shift B to the power of -1 times the mass matrix as an eigenvalue problem, and we are solving this this eigenvalue problem using a MAMS LU factorization, essentially. Well, we are using that as the preconditioner for my Krylov solver, but it doesn't change much. And yeah, and the algorithm I'm using is Arnoldi to solve. We have many options: Arnoldi, log-PCG. Anybody of you that is familiar with SLAPC know that there are many SLAPC solvers wrapped in there. You can also do, well, you will soon be able to do also nonlinear eigenvalue problem, but I'll come to that in a moment, which is this, the future feature. So, ngSolve matrices, right now we inherit a lot of information from the bilinear form when we assemble a Krylov solver. So symmetry, for example, is inherited there, and we tell PETSI you are working with a symmetric matrix. In particular, we tell it SLAPC when we work with eigenvalue problem. We do not inherit the basic, so the block structure. If we get a base matrix with a block structure, we don't know what to do with it right now. But since we now can work with square matrices, we're able to transform it in PETSI nest matrix, and this will allow for field splits preconditioning directly in PETSI, which is, for example, Andy Wotton idea of preconditioning with the mass matrix. So a bit of Oxford flavor. Then we have, we would like to wrap PETSI's nest, which is non-linear solver. Why? Because you have easy access to line search and trust region, which are, as Richard was saying, extremely important when it comes to solving PD. We would like to wrap PETSI-TC in future, which is the time stepper, directly wrap into PETSI. There are a lot of them. And then the PEP, the polynomial eigenvalue problem. The PEP is really there. I need to push. And then the secret. Now that you have NGS PETSI, don't tell Joachim, you can use NetGen meshes also in Firedrake and Phoenix. And this was one of the motivations for doing this. And that's it. It's as easy as asking NetGen to give us a mesh, Firedrake mesh. Now we can run on Firedrake with that mesh. And since I've seen somebody else speaking about Firedrake before, I included a code snip. Yeah, that's it for me. If you want to see more detail about this, come to the tutorial tomorrow.
Thank you very much. It's definitely very interesting. Then Jen, we are in touch about close to 10 years. Then Jen is an MIT graduate developing his finite element package and using NetGen for a while. And will present the new design of Welsim.
Thank you, Dr. Scobrel. My name is Liang. I'm the founder of the Welsim. Very honored and delighted to be here on this beautiful campus and talk about my work and research. I have two topics here, but both topics are related to the engineering simulation software, and also both highly relevant to NetGen and ngSolve. So I think it's a good idea to just put together in the one slide. In the part one, I talk about using NetGen library in the engineering simulation software, basically in my own product. And NetGen, I think it's very famous, and in the simulation community, nearly everyone knows NetGen. And heard about the NetGene. NetGene has many merits. It's open source, freely licensed, easy to use. No matter if you're an end user or the UI developer, try to integrate the NetGene with your own product. And it supports multiple input formats like STEP and STL. The both formats are commonly used in the industry. STL for the CAD format, STL with the merging of 3D printing technology, and lots of people use the STL. And I have applied NetGene as a sole measure in my product for years, maybe 6 or 7 or 10 years. So then it works very well. It turns very good idea, and the mesh quality very good, and I can mesh different from simple or complicated geometries. Both can handle very well, and performance is good. My implementation is very straightforward thanks to the good interface of the NetGene. Basically, let's see. Did I skip one? Interesting. Seems I missed the one page, but it's fine. Okay, so let me see. Okay, this I don't know why. For some reason, this page go to this one. Okay, so I created a console program. It's called WS Mesh, and this mesh basically built on the top of the NetGene. We see these two dependents, the ng-libs and ng-core, like Christopher just talked about. This is the kernel of the NetGene. And my app is my main program. It basically has a GUI. We just click the meshing button on the screen, then can start this. My app going to start a child process of the WS mesher and do the meshing job. So this is how the workflow goes. Let me just go back to.
Program is called Welsim.
Yeah. Product is Welsim. Yeah. So yeah, I just use my app here. Yeah, thank you. So we use the executable program. We always care about input and output. So the input file here has two types of files versus the shape files. Basically, I prefer the STEP and STL. And depends on the model. If the assembly could have like lots of files, lots of shapes. So it could be like 10 shapes files. And I also have one control file, which is a JSON file. And the format looks like on the right side. Basically defines some key information like a dimension, a working directory, length unit something, and each region. This region is a vector, so each region we define, we give the parameter, the meshing parameter to the NetGene to consume. So this allows each shape can mesh with different mesh densities. Yeah, then WS mesh is read the file. The output has two files as well. One is the mesh file, which is in the UMV format. Depends on how many shapes. If I have 10 shape files, now I will generate 10 UMV format mesh file. Then I also have another file called shape to mesh data. Let's say we have one shape, then each shape has sub-shapes. So each sub-shapes, we need to know which elements are touching to that sub-shape. So this sub-shape could be the face, could be edge or vertex. Once we have this data, let the GUI to read this output, then we have all this data and they are assembled together. Then later the user can select the face and generate boundary condition or contact face, then can easily achieve that. So this is my way to use the NetGene. Could be multiple ways, could be some ways even more advanced. And NetGene has GUI, very easy to use, and any user can directly use GUI then to do the meshing work. The second part I'll be talking about RPC-based architecture of the general purpose engineering simulation software. Is my latest research. And since the name is so long, so I just make a short name called GPGIPS, called it in my slides. So there's a very beautiful history about the GIPS. We see in recent nearly 100 years, maybe start from recent 80 years, lots of smart people and hardworking people working in this industry, and this industry is still growing, growing very fast. With time goes by, we see the people's care is from the correctness and accuracy, and move to more kind of coverage on different physics problem. Then recently, let's say, start from 21st century, people start to focus on user experience, make the software very easy to use. Even people don't have PhD can use the simulation and get good solutions. Recently, I feel like when I do some research, I found the simulation software become more flexible. Then in another word, it could become agile. Users require, hey, your product not only can do on the desktop, but also can support the web UI or cloud computing. And right now we know that AR is very popular, it's booming technology, also VR. How the simulation software can support this or embrace this kind of new technology, that requires your software must be agile. There's no very straightforward standard in the industry right now. We have to design our own architecture or customize the architecture. And plus, if we have lots of legacy code, how we integrate the legacy code and to adapt to this new trend. So I design a system and use a WebSocket, an RPC interface, and hopefully it can address that. It's just designed right now. I haven't implemented it yet. I have to do it one step by step. Any large scale software has multiple process. For the simulation software, when it becomes bigger, we need handling all these different process, how this is communicated, how we initiate it, how we launch it and close it. So here in my case, we start with myapp.exe, and we started, and we initially instantly launch several other child process. Particularly the daemon exe is a very important controller. And once daemon started, and we'll launch another child progress, another different, let's say the solver child progress and nodes and measures. And this definitely, the solvers can be built on the ngSolve, the measure can be built on the NetGene. This all child process or grandchild process and stay with the main program, myapp. And when I close myapp, I need to close the grandchild first, then close the child, then close myself. So we don't want to leave any child live there when my program already shut down. So each is the grandchild process is doing their own job. They will do solve work. When we have this progress architecture, and we want them to communicate it well in a very efficient way. First, I start WebSocket service on the daemon. So daemon's kind of controller very important. So this is WebSocket communication. It allows a permanent connection. So once the handshake, the permanent connect, and it allows the bidirectional data transformation. Then it supports different kind of UI. So basically, the daemon is kind of server, and the UI are kind of different clients. Then the communication data is based on a JSON format. If the big data, we just generate like a big file, binary file, and give the address to the clients. So one of the big benefits of doing that is we can support different kind of GUI. No matter it's a desktop GUI, cloud GUI, or web GUI, it's very flexible. So no matter what kind of language you use, Python, C, JavaScript, all supported. So that's kind of flexibility that we create if we use the WebSocket communication. In addition to the WebSocket, and also each like a solver or the mesh, the grandchild, we provide the RPC service. This is a very dynamic way to create a communication. It's based on request and response, and not only to support the networking communication, but also the local communication for different process. Once we start service, so we start to listen, open the port, and listen to the clients to give any request. The written JSON data file also include a field that indicating the call is failed or succeed. So basically, we are RPC, and definitely we need to write lots of synchronous functions. That's a lots of writing or programming work we need to do. That basically Python and C can easily achieve that. Then we need to write a router to translate a different address, basically the string into the function, and we need to write a very important function called the state change, then to return the payloads of the RPC, let the clients know what's happening and what we're going to do next. Also, some security concerns, like we can use TLS certificates, and also we can determine which port we can open to different clients. That's basically design. This already talked it. So make a quicker conclusion. NetGene has been proved by the industries. It's pretty good mesh generator, and mesh complex. It's able to measure the complex geometries, easy to use. Also, The object-based architecture I proposed here, I can make the chips very agile. Also can apply this architecture to a different larger scale software. So yeah, this conclusion in the future, I need to do something else to improve the mesh I/O performance with netting, design today and yesterday I learned a lot about the netting. So maybe I can try to design software handshakes with netting. So yeah, that's pretty much of this. I thank Dr. Scobell and Dr. Gopal Krishnan, and also entire NG groups. Let me to present my work. And also thank Websum users and partners and investors. Thank you guys.
A short question, sir. I know Delsim is not the most expensive software, but do you have also university licenses which are free?
Dr. Scobell, if you need, we definitely will provide it for free for you. And if any, since here is from the NGSoft group and no Dr. Scobell, so yeah, we'd like to give you the collaboration license, which could be, could be free. So, thanks.
And next talk is
Sorry to take a bit of time out of your coffee break, but I'm going to just do this real quick. Yeah, okay.
Great, fine, good. Peter Vandenberg, best student of J.
Yeah, Peter Vandenberg. Thank you, everyone. Okay. Let's see if this talks to this. Great. I remember earlier this was not having a lot of success in mirroring, so I'm going to be doing a little bit of head turning during this whole presentation. Hopefully you'll accept that. So thanks everyone for having me. I'm just going to, I created a tutorial. So we can do that later today or tomorrow if you want, mostly about using ngSolve special functions. Yes.
Could you increase the zoom level?
Oh, yes, I believe I still can. Yes, great. Is that good? Yeah. So if you haven't yet, go ahead and go to this page, download special functions and install it. That'll allow you to visualize Bessel functions. So Bessel functions, Henkel functions, other special functions exist and are solutions to the radial portion of the wave equation. I'm not quite sure what that was. So once you have got that installed, you can open up JV here and plot it on a nice circular domain. And if you, this is getting the tricky part, if you deform it, it should look basically like a vibrating drum head. Yes. Okay, so I use these all the time, primarily in solutions to another wave equation, in this case, electromagnetic field equations, in waveguides. And so primarily today we're going to talk about using these for visualizing the fields. So if we go here, we're going to look at this device here. Now, this device doesn't look like much at the moment, but this is a circular ring of glass in air, suspended in air inside and outside. And we're going to try and model propagating electromagnetic fields, assuming perfect directedness along the z-axis, aka out of the plane here, and time harmonic as well. So if it turns out that for modes of these devices, you can actually find them exactly, semi-analytically. And so you can get an eigenvalue equation, and for each complex number in the plane, when you find a zero of that equation, that gives you a mode. It gives you something that propagates in this device. And so here is one of those. Let's get to, I have to get rid of something to find full screen, don't I? No. I want to go full screen. Is it just as simple as going Control F? No. Oh wait, that's because I'm zoomed in that I don't see it. There we go. Okay. And so here's a sample longitudinal component of the electric field for one of these modes. This has a bit of a strange characteristic in that it has very high number of ripples in the high index region. If I go ahead and deform that somewhat.
Maybe complex animated is also good.
You want to see it?
Yeah.
Okay.
Oh, wow.
That's the real part. That's going to be at 90 degrees to it. This shouldn't do anything. Yeah, that didn't do anything, the norm of it. Yeah, it's a bit different than we might have expected. This is the longitudinal component, not the transverse, which might get more of an in and out kind of a situation. Okay, and so one of the things that happens in these waveguides, so this is in the outer region here, we have Hankel functions. On the inner region here, it's a combination of the Bessel functions. On the inside region, it's a single Bessel function with a azimuthal radial dependence, just cosines and sines. I want to stop this animation because it's gonna
Switch off second.
There it is. Okay, and there's the transverse portion of it. Maybe this is what we want to complex animate, although I already have the norm here, so that's not going to do much. I'll just deform it a little bit. We actually, even in the transverse component, we have some of these sort of high frequency oscillations in the high index regions. Okay, so one thing that happens with these waveguides is if you put different input frequencies into the waveguide, you have spikes of loss. I'm glad you're nodding like that over there. Yeah, you have loss spikes at certain input wavelengths.
I do work in a similar field, so yeah.
Nice, nice. And so what we were looking at actually is a pretty well-behaved mode. If we go back into here, that's a well-behaved mode. But if we could do cross sections of that mode, and I have just that is a bit strange. Why is it looking like that? Don't tell me something's off here. Let me rerun something up here for a moment. Yeah, something's off. Okay, let me just rerun things. Yeah, you like all that. Now it's beautiful. Okay, beautiful again. Maybe now you'll be beautiful again. Yeah, you're beautiful again. Okay, there's the Z component cross section. There's that. But let's look at what happens. And this is a nice mode. This is a nice mode cross section. Let's see what happens at a resonant mode cross section. So one of those spikes. Resonant. First of all, we're going to see that when we look at the eigenvalue equation, when we look at the modes, things have gone quite wonky. Like you should have a mode that's pretty close to low loss. All the modes have high loss, aka they're off the real axis. And if we look at the, oh, I already have them here. If we look at the Z component of it, we've lost most of the interior of the Z component. We're all just extreme fluctuations in the high index regions. And out here, if you look at the transverse component of it, you can see that all your energy is leaking out, actually. So let's see. I don't know if this reads leaking out energy to everyone else, but it does to me. So let me turn down the deformation even a little further. Oh, that's not going to work. So subtle. That's the best I can do. Okay. And zoom out. Come on. Oh, it's having trouble. So when you have a resonant input frequency, you're no longer containing most of your energy inside this guiding region. You're allowing, through these ripples, this standing wave now, the energy to go out to here. So this is the pointing vector, the transverse component of the pointing vector. Okay, and if we looked at the 1D cross sections, we would see even a little bit more. So this nice contained mode at a nice wavelength, and this leaky, well, they're all leaky modes, but this is leaking even faster. We use, besides ngSolve for simple visualizations, we're using it as well to capture the modes again, using Nadelic elements in the transverse portion, Lagrangian elements in the longitudinal direction. And as you might imagine, capturing those high frequency oscillations is difficult. So you have to bump up your number of elements in those regions. You may have to bump up your order of your elements as well. This is still pretty far from convergence, but it's what I could do quickly on my local computer. And we're working on adaptivity schemes in our group to address this as well. One thing I wanted more to show you before we break for coffee is there was a question yesterday about the strength of the PML, the necessity for strength of PML before you've achieved what you need to achieve. And with these particular fibers where you have radial symmetry, you can actually find the mode semi-analytically, but you can also find the mode semi-analytically with PML and with perfectly conducting boundary conditions. And so here's a mode in its standard way with no PML, no perfectly conducting boundary conditions. And in this case, we have the mode guided in an air region, and there's a high index region out here. If we add in PML with a strength alpha of 0.06, it actually doesn't change the eigenvalue equation whatsoever, which we would predict and hoped. But with our visualization tool now, this, and I should go up here, let's go back up to here. If I turn on the norm of this, this is what we see, a bit of deformation here. So this is the mode without any PML added and no perfectly conducting boundary conditions. It would be 0 on the boundary otherwise. If you add PML in, you can start to see, well, okay, I haven't instituted perfectly conducting boundary conditions, but I see that the PML is making my function decrease. So that's good. I could use this to decide what strength of PML I need, because I should be getting down to 0 here. If, let's see what strength I need. So, oh, excuse me. If we add in PEC conditions, we can see if I add a 0 PML here, so I've zeroed out my PML and I plot the determinant, my mode has become lossless, right? I have a perfectly conducting layer on the outside, and without a PML, I've lost all information about the leakiness of this mode. But if I add just a bit of PML into there, it goes off the real axis and approaches the correct value of loss. So if I go through here and I look at what happens here, we can see now that I have a good, or I'm getting there. It's still not quite perfect. So I'm decreasing, but I still have some ripples in my PML region. I should probably turn up my PML just a bit more. In address to that question yesterday, I think it was Peter who asked this about the strength of the PML. You can actually do, for this fiber, a run through and see for different wavelengths I have different loss values, and with a particular value of PML I haven't actually achieved convergence. I haven't found my correct loss values. So the exact loss is here. The exact losses I'm getting but with PML not strong enough are actually wavelength dependent. And if I go through a bunch of runs, I can see for different values in my PML alpha how strong I need to get it until it converges to my exact loss value. And it's actually not very strong. You don't need to be very strong. So go get the special functions add-on to ngSolve, and it'll allow you to view all these things. Thanks so much. I'm going to clap for myself. Cool.
Yes.
Yeah.
Thank you. Super. Okay, now let's have a coffee break, and the next item on the point is some open discussion round, suggestions, what you think, some feedback, what are plans. Maybe the coffee break now and restart the quarter past. Maybe announce for the dinner already now. So we have the dinner starting at 6:30, and I think we will be there by 6:15.
Hey everybody, this is the important.
Attention,
Involves
most
dinner.
important is
So as soon as it's 5, we should get out of this room. But there are open spaces down on the second floor where you can continue the discussion. And around 5:45 or so, we just start getting towards dinner, so as to reach 6, but not later than 6:15. And you can hang out there, and food will arrive half an hour later.
Where is dinner?
The dinner is in Hotel Zen.
And it starts at.
At
It
6:45.
really starts at
6:45.
6. Okay.
No, I note the schedule says dinner starts at 7, so don't show up when the schedule actually says. That's important.
And is it catered? Does it arrives? The food arrives or do we order?
I think it's.
Hey, yeah. No, I really was happy about that. I was like, somebody knows exactly what it is. Awesome.
We mainly do spheres, making out of spheres, suspended in vacuum.
Gallery waves, whispering gallery levels and stuff.
It's very related to that.
Yeah.
It's basically the same idea. And my application is more optical,
Well, this is like, oh yeah, I guess that is amazing.
Yeah, but I mean,
yeah. Although this was vector. Yes. Oh, yeah, yeah. Oh, thank you so much. Where are you? Oh, awesome. We're set. That's the most recent one. I've heard about that. Yeah, seems cool. Like a upstart kind of thing. Yeah. Yeah. So at one point, somebody came here, went out here. He was, I forget her name, President Matt.